Hello, you're listening to Night Cosmos Sleep, where we leave familiar sounds behind and journey into the distant reaches of the universe. On this journey, we will visit WASP-76b, a world located about 640 light-years from Earth. It is so hot that iron can turn into vapor, be carried toward the dark side by powerful winds, then gradually cool and fall as droplets of metal. And yet, in the midst of such an extreme world, telescopes have detected a very different kind of light. It is faint, multicolored, and may resemble a glowing arc appearing near the boundary between day and night. Is this light truly being created by droplets of iron? Or is WASP-76b still hiding another secret within its atmosphere? To begin this journey, we will follow the first clue that drew astronomers' attention to this distant world. That first clue was not a clear image of the planet, nor was it a photograph of metal rain falling through the darkness. It was only a tiny change in the light of a star located in the region of the sky belonging to the constellation Pisces. The change was far too faint for the human eye to notice, but to sufficiently sensitive telescopes, it appeared as a steady rhythm of dimming. From that fragile pulse of light, WASP-76b began to reveal its existence. From Earth, we cannot see this planet as a separate sphere suspended beside its star. At a distance of nearly 640 light-years, WASP-76b is lost within the glare of its host star and can only be detected through indirect traces. Each time the planet passes in front of the star, it blocks a portion of the light, causing the brightness of the entire system to fall very slightly. When the planet moves away, the light returns to its original level, like a shadow quietly passing in front of a lamp in some distant place. The change is small, but it repeats with a steady rhythm, allowing astronomers to recognize that a giant object is moving around the star. From the depth of the dimming, they can estimate the planet's size. From the time between one drop in brightness and the next, they can determine how long a single orbit lasts. And from the tiny variations hidden within that signal, they gradually realize that this world was far stranger than a dark point, simply crossing through the light. WASP-76b is not a rocky planet with mountain ranges, valleys, or oceans beneath a clearly defined sky. It is a giant gas planet, larger than Jupiter, but orbiting far closer to its star. In the atmospheric layers that telescopes can observe, temperatures rise so high that many familiar materials on Earth can no longer remain in their usual states. Metals that are hard and heavy in everyday life may become part of the atmosphere, drifting within the currents that circle the planet. Iron is one of those materials. On Earth, we usually think of iron as something found in rocks, buildings, or objects we can hold in our hands. But on WASP-76b, some regions are hot enough for iron to exist as a vapor, blending into the atmosphere much as water can rise from the surface of an ocean. It is a difficult image to grasp through ordinary experience, because on this world, entire regions of the atmosphere may reach temperatures comparable to the most powerful furnaces humans have ever built. Even so, astronomers have never directly seen an iron atom drifting through the atmosphere of WASP-76b. They have never photographed a metallic cloud or a falling droplet of iron. What they observe is the light of the star after it has passed through the thin atmospheric layers around the edge of the planet. Along that journey, certain narrow colors are absorbed by atoms in the atmosphere, leaving behind distinctive gaps that instruments can detect. Every element leaves its own signature in light, much as every voice has its own tone. By separating the light into extremely detailed bands of color, astronomers can find the signs of iron, even though the planet itself remains only a tiny point that cannot be seen clearly. Light, therefore, becomes the only way to enter the atmosphere of WASP-76b without actually traveling there. It reveals which materials are present, how they are moving, and sometimes even the differences between one region of the planet and another. That difference led to the first mystery. The signature of iron vapor did not appear in the same way along both edges of WASP-76b as the planet crossed in front of its star. On one side, the iron signal appeared more clearly, while on the opposite side, it weakened or nearly disappeared from view. This imbalance suggested that during its journey through the dark side, the iron may have changed state and left the atmospheric layers being observed by the telescope. From this, a remarkable picture began to form. Iron may be heated on the day side, mixed into the atmosphere, and then carried toward the night side by powerful winds. As the temperature falls, the iron vapor may condense into small particles or droplets and sink into deeper layers of the atmosphere. We call this possibility iron rain. Although the rain may not fall onto solid ground in the way familiar rain falls on Earth. On a gas giant, there may be no clear boundary between sky and surface. Deeper down, the atmosphere becomes denser and the pressure rises, allowing falling droplets to change further before reaching any layer that might be called a surface. The image of iron rain, then, is not necessarily a scene of metal droplets striking glowing red ground. It may simply be the formation of iron particles within the atmosphere, falling deeper until they disappear from the region that starlight can pass through. The important point is that no human being has ever directly seen this rain. It is inferred from the way the iron signal changes as the atmosphere moves from the illuminated side into darkness and then returns again. It is a little like seeing dark clouds and hearing water falling behind a closed door. We can understand what may be happening without watching every drop. Even so, every explanation must be tested through many different observations before it can become a reliable picture. If the story of WASP-76b ended with metal rain, the planet would already be unusual enough to study for many years. But when telescopes followed its brightness through an entire orbit, another signal appeared. Near the boundary between the bright side and the dark side, the light increased in a way that did not fully match the predictions of simple models. The difference was very small, but it repeated clearly enough to draw the attention of scientists. It was not a flash of lightning erupting in the atmosphere, nor an explosion that caused the planet to blaze for a moment. It was simply a little more light than expected, appearing when WASP-76b reached a particular point in its orbit. This suggested that one region of the atmosphere might be reflecting light more strongly than the others. The way that light seemed to gather along the viewing direction brought to mind a rare optical phenomenon known as a glory. On Earth, a glory can appear as small colored rings surrounding a person's shadow on clouds or mist. It is not quite the same as a familiar rainbow stretching in a broad arc across the sky, but it still creates delicate bands of color through the interaction of light with tiny droplets in the air. For the effect to appear clearly, the droplets need to be nearly spherical and relatively uniform in size. That requirement makes the possibility of a glory on WASP-76b both fascinating and difficult to explain. The atmosphere of this planet is not a peaceful place. Temperatures vary sharply from one region to another. Gases may move at tremendous speeds, and clouds may continually form and disappear. In an environment like this, maintaining droplets uniform enough to create a clear ring of light would not be easy. If the signal truly comes from a glory, it would suggest that a more stable cloud region can exist within this violent atmosphere than we once thought possible. Liquid iron is one of the possible materials that has been suggested for those droplets, because iron may exist as vapor in hotter regions and condense as it moves toward cooler areas. Metallic droplets could form near the boundary between day and night. If they were the right size, starlight could interact with them and produce part of the signal recorded by telescopes. Even so, this remains only a hypothesis, and there is not yet enough evidence to confirm that the glowing rings are made of iron. The clouds on WASP-76b may contain some other material, or the unusual light may come from a temperature pattern that is not yet fully understood. A brighter atmospheric region, a strongly reflective cloud layer, or an unusual wind structure could also alter the planet's light curve. For that reason, the phrase metal rainbow should be understood only as an image that helps us picture the idea. It does not mean that astronomers have actually seen an iron rainbow suspended above the planet. The two mysteries of WASP-76b are therefore both built from indirect evidence. The iron rain is inferred from where iron vapor appears and then disappears, while the multicolored glow is suggested by a slight increase in brightness near the boundary between day and night. The two may be connected to the same process, as material moves from hotter regions into cooler ones and begins to condense, but they may also be separate phenomena that happen to appear in the same part of the atmosphere. This is what makes WASP-76b far more interesting than a list of extreme numbers. The planet is not merely hot, large, or fast-moving around its star. It may contain distinct climate regions, winds that carry metals across the atmosphere, clouds that change with temperature, and optical effects that appear only when we view them from the right angle. A tiny point of light has begun to emerge as a world with motion, weather, and mysteries that still remain unexplained. From a distance of nearly 640 light-years, every trace of the planet must cross an immense stretch of space before reaching Earth. The photons collected by telescopes today left that star system centuries ago, carrying only a very small piece of what was happening in the atmosphere. They do not bring us a complete image, but each photon preserves a little information about its direction, its color, and the matter it encountered along the way. When millions of signals like these are placed together, the story of WASP-76b gradually becomes clearer. The first thing that may draw attention to the planet is its temperature, high enough to turn metals into vapor. But the heat only opens the first door. What is truly strange is the way light, darkness, and matter are divided between two nearly opposite regions, while the atmosphere continues to connect them. One side may keep iron in a gaseous state, while the other may cause that same material to condense and sink. Between those two regions lies a transition zone stretching around the planet, where light gradually gives way to darkness, and atmospheric currents carry material from one side to the other. It may be here that metallic clouds begin to form. It may also be here that a rare optical effect appears, sending a tiny portion of its light toward Earth. To understand why the two halves of WASP-76b can be so different, we need to look at the rhythm of motion that keeps one side of the planet in permanent light and the other in lasting darkness. Because on WASP-76b, everything begins with an orbit so short that an entire year ends before 2 days have passed on Earth. It is from this unbelievably short orbit that the story of WASP-76b begins to come into clearer focus. On Earth, we need 365 days to complete a year. On this distant world, an entire journey around the star lasts only about 43 hours. In less than 2 of our days, the planet completes the full distance of a year and returns to where it began. Imagine a clock whose year hand moves faster than the familiar day hand on Earth. By the time we wake up, move through a working day, and reach the following evening, WASP-76b has nearly completed another orbit. Its motion is so rapid that ideas such as seasons, months, and years, which feel so natural to us, almost lose their familiar meaning. The reason lies in the distance between the planet and its host star. WASP-76b does not travel along a wide, cold orbit like the gas giants in our solar system. It lies extremely close to its star, making the path of each orbit much shorter. At the same time, gravity at that distance pulls the planet along at tremendous speed, allowing an entire year to pass in little more than a day and a half. To understand how different this is, we can look toward Jupiter. The familiar gas giant in our solar system lies much farther from the Sun than Earth, and takes nearly 12 years to complete a single orbit. A child born on Earth may reach the beginning of adolescence before Jupiter finishes 1 year of its own. On WASP-76b, By contrast, thousands of years would pass over the span of a human lifetime. Our Jupiter exists in a region distant enough for much of its atmosphere to remain far cooler. Its clouds are made of substances that can condense under cold conditions, while sunlight appears as a smaller source of brightness in its sky. WASP-76b exists in almost the opposite environment, where the star fills a much larger portion of the view and continuously pours energy into the atmosphere. Planets like WASP-76b are often called hot Jupiters. They are gas giants similar in size to Jupiter, but they orbit so close to their stars that their temperatures rise to extreme levels. The name does not describe an entirely different kind of matter. It simply refers to a giant gas planet living in an environment far hotter than anything found in the outer regions of our solar system. WASP-76b belongs to an even more extreme group, sometimes called ultra-hot Jupiters. On worlds like these, daytime temperatures can rise beyond the point where many molecules can preserve their familiar structures. Some compounds are broken apart, metals can appear in the atmosphere, and clouds may form from materials very different from water or ice on Earth. Interestingly, WASP-76b is not more massive than Jupiter. Its mass is slightly lower than that of the largest planet in our solar system, yet its size is considerably greater. This makes it resemble an enormous sphere of gas that has been inflated, with outer atmospheric layers extending much farther than might be expected from its mass. Much of that inflation is connected to the intense heat the planet receives. When an atmosphere is heated continuously, its gas particles move more rapidly and occupy more space. The outer layers expand, increasing the planet's radius without a corresponding increase in mass. WASP-76b therefore becomes an enormous world with a lower average density than Jupiter. We might picture it as a ball of gas placed beside a powerful source of heat. It is not empty inside, but its outer layers spread outward and become more extended. On WASP-76b, this process does not last for only a few minutes or hours. It has been sustained for millions of years beneath the constant light of the host star. If it were possible to stand within a sufficiently high layer of the atmosphere and look toward the star, the sky of WASP-76b would appear very different from Earth's. The star might look far larger than the sun does in our sky, not necessarily because it is extraordinarily larger, but because the planet lies so much closer. Light and heat would arrive from a broad region overhead, making the distance between the two bodies seem almost non-existent. Of course, there is no stable place where a person could actually stand and observe the view on this gas giant. The outer atmosphere is always moving. The temperatures are extreme, and pressure rises rapidly with depth. Still, the image of the star hanging enormous in the sky helps us understand why WASP-76b receives so much more energy than Earth. Its close distance means that every square meter of atmosphere is exposed to an intense flow of radiation without interruption. That energy does not merely warm the planet slightly, it heats the gases until many materials change state. Molecules are broken apart, and elements found only in rocks on Earth can become part of the atmosphere. WASP-76b is not hot because it is burning from within. There is no enormous flame covering the planet, and no combustion process consuming fuel in the atmosphere like a furnace. Most of the heat comes from the planet's extreme proximity to its star, and the constant absorption of the energy the star releases. This distinction matters because the word hot often makes us think of fire, but matter throughout the universe can reach very high temperatures without any flame appearing at all. The atmosphere of WASP-76b is heated by light and radiation, much as an object warms beneath sunlight, except that here the distance is so small and the energy so intense that every process is pushed toward an entirely different limit. The star does not simply heat the outermost layer and stop there. Energy is absorbed at different altitudes then transported and redistributed by the atmosphere. Some heat moves deeper. Some is radiated back into space, and some is carried to other regions by powerful winds. The climate of WASP-76b is therefore shaped by a continual balance between incoming energy, escaping energy, and atmospheric motion. Its close orbit also makes the planet's motion very different from Earth's. WASP-76b travels around its star at tremendous speed, but from the planet itself, the star would not race across the sky, as we might imagine. Over a very long time, gravity has altered the planet's rotation, gradually bringing it into a state where the same side always faces the host star. Before reaching that result, it helps to remember that every planet both orbits its star and rotates around its own axis. Earth completes one rotation in about 24 hours, creating day and night, while taking 1 year to travel around the Sunday. These two rhythms are very different and are not locked together. WASP-76b may once have rotated at a different rate, but because it lies so close to its star, gravity does not pull equally on the near side and the far side of the planet. That slight difference creates tidal forces, which gradually drain rotational energy and adjust the planet's spin over immense spans of time. The process does not happen suddenly. There is no moment when the planet abruptly stops and turns in another direction. Over millions of years, its rotation slows or changes until it becomes synchronized with the orbit. Eventually, the time WASP-76b takes to rotate once becomes exactly equal to the time it takes to complete one journey around the star. This means that one rotation of the planet also lasts about 43 hours. But because the planet moves around the star at the same rate, one side continues to face the source of light at all times. It is similar to the way the moon always shows Earth nearly the same face, even though it is still rotating throughout its journey around us. Seen from the outside, WASP-76b is still spinning and moving without pause. But for any point on the planet, the star's position in the sky would remain almost unchanged. Near the center of the day side, the star might hang high in the same region forever. On the opposite side, there would never be a moment when it rose above the horizon. This is where the idea of a 43-hour year begins to mean more than a simple number. It does not only reveal how quickly the planet moves around its star, that orbital rhythm also determines how light is distributed, creating one half of the world that is continuously heated and another that always faces away into space. On Earth, every region passes through light and darkness in turn. Even places with long seasonal days or nights eventually experience change. Because of this alternation, temperatures have time to rise and fall. The atmosphere is mixed more evenly, and no region receives uninterrupted sunlight for millions of years. WASP-76b has none of that familiar balance. Light does not sweep across the entire planet from one day to the next. It remains concentrated on one side, while the other never sees the star directly. This creates an enormous imbalance in energy, becoming the driving force behind powerful winds and the movement of matter between the two regions. We might imagine that the dark side must be cold enough to freeze, but WASP-76b lies far too close to its star for that to happen. Its thick atmosphere and powerful winds carry enormous amounts of heat from the day side to the night side, keeping even the regions without direct starlight far hotter than anywhere on Earth. The contrast is not between hot and cold in the familiar sense, but between one region that is extremely hot and another that is somewhat cooler, yet still intensely heated. That difference is still enough for iron to change state. In the hottest regions, iron can exist as vapor. When winds carry it toward the dark side and the temperature falls, it may begin to condense. The night side does not need to become cold by Earth's standards. It only needs to cool below the point where iron vapor can remain stable. The short year of WASP-76b does more than turn the planet into a rapidly ticking cosmic clock. It places the world close enough for its atmosphere to be heated with extraordinary intensity and, through tidal forces, keeps one side permanently facing the star. From that arrangement, every unusual phenomenon we are following, from powerful winds to iron rain, begins to find the conditions it needs to form. But the presence of such a large gas planet so close to its star raises another question. Giant planets are generally thought to form farther out, where enough cold material is available to build a large core and attract thick layers of gas. If WASP-76b also began its life at a greater distance, it may have gradually moved inward before settling into its present orbit. There is no need to follow that journey too deeply, because we cannot reconstruct every stage of WASP-76b's past. The planet may have interacted with the disk of gas and dust surrounding its young star, or the gravity of other bodies may have altered its orbit. What matters is that its present location may not be where it was born, but the final destination of a journey that unfolded during the early history of the system. Once it moved close enough, new conditions began reshaping the planet. Its atmosphere expanded under the intense heat, its rotation gradually became locked, and each orbit grew unimaginably short. Whatever WASP-76b may once have been farther from the star could have changed profoundly, leaving behind a world now almost rebuilt by starlight and gravity. Perhaps this is what makes a 43-hour year more meaningful than the number first suggests. It does not only tell us how quickly WASP-76b moves, it also reveals its extreme proximity, the enormous amount of radiation it receives, its expanded atmosphere, and a history in which the planet was gradually forced to move in rhythm with its star. From Earth, we detect that rhythm each time the planet passes in front of its host star. The light dims, returns to normal, and then, only about 43 hours later, the same signal appears again. One year ends and another begins, repeating so quickly that astronomers can observe many orbits within a relatively short period. That rapid repetition also helps us study the planet more clearly. Every transit offers another opportunity for starlight to pass through the atmosphere and carry back additional information. Each orbit allows researchers to test whether the iron signal, the brightness, or the properties of the clouds have changed. The world moves quickly, while human beings quietly collect each pulse of light and use it to reconstruct the planet's climate. Yet while one year after another begins and ends on WASP-76b, the sky above each side remains almost unchanged. The star continues to hang over the same region of the day side, while darkness remains fixed over the opposite hemisphere. Time passes rapidly through the planet's orbit, but sunrise and sunset do not come and go as they do on Earth. This is the planet's next paradox. It races around its star at tremendous speed, yet in its own sky, the source of light may appear almost motionless. A year passes in only 43 hours. But in many places, day or night continues without end. For millions of years, gravity has preserved this division. One side remains permanently exposed to the light, where the atmosphere is heated until metals can turn into vapor. The other side always faces the darkness, where winds carrying material begin to cool during their long journey around the planet. WASP-76b is therefore no longer simply a sphere of gas orbiting very close to its star. It becomes two neighboring climate regions connected by winds that never stop moving. To understand where iron rain may form and why an unusual glow might appear near the planet's boundary, we need to look more deeply into this division, because ever since the planet's rotation fell into step with its orbit, one half of WASP-76b has remained forever beneath the light, while the other has never seen its star rise. Ever since WASP-76b's rotation fell into step with its motion around the star, the planet's sky has remained almost unchanged. One side is always flooded with light, where the star hangs high and never sets. The opposite side has no dawn, no moment when the first trace of brightness appears along the horizon. Between these two regions lies a band of endless twilight stretching around the planet, quietly dividing light from darkness. This image may seem difficult to understand because WASP-76b is still moving extremely quickly. In only about 43 hours, it completes one orbit around its star and immediately begins another year. A world moving so rapidly might be expected to see day and night constantly changing places, yet in its sky, the star remains almost motionless, while the bright and dark hemispheres have stayed in the same positions for millions of years. The moon can help us picture this more clearly. When we look into the night sky, we almost always see the same face of the moon turned toward Earth. Its familiar dark regions, craters, and brighter patches appear in nearly the same places. The far side remained a mystery for a very long time, until spacecraft traveled around it and captured the first images. The moon is not motionless, nor has it stopped rotating. It continues to spin on its axis while traveling around Earth. What makes it special is that these two motions take nearly the same amount of time. After completing one orbit, the moon has also completed exactly one rotation, allowing the same side to remain turned toward us. WASP-76b follows a similar rhythm. In the time it takes the planet to complete one orbit around its star, it also rotates exactly once on its axis. Every part of the atmosphere is still moving through space, but that motion is just enough for the side facing the star to keep the same orientation. One half of the planet therefore lives beneath an endless day, while the other remains permanently in darkness. This state is known as tidal locking. The term may sound unfamiliar, but the process behind it begins with something fairly simple. The star's gravity pulls slightly more strongly on the near side of the planet than on the far side. That small difference stretches the planet, gradually alters its rotation rate, and dissipates some of its rotational energy over an immense span of time. There was no moment when WASP-76b suddenly stopped rotating. Its motion simply slowed or adjusted little by little across millions of years. Eventually, its rotation period became exactly equal to its orbital period, creating the stable state we observe today. From that point on, light remained concentrated on one side, while darkness held the other. Near the center of the day side, the star may hang almost motionless in the sky. Its light does not gradually tilt toward afternoon or turn red before disappearing. The atmospheric layers there continually receive energy from the same direction, with no nighttime interval in which to cool. Over time, this region has become an enormous furnace extending across nearly half the planet. Temperatures in the atmospheric layers we can observe may reach about 2,400 degrees Celsius. At such heat, many materials exist in forms completely different from those familiar on Earth. Metals that are solid here can appear as vapor. Some molecules are broken into simpler components, and the atmosphere becomes filled with materials we usually find only inside rocks. The figure of 2,400 degrees does not describe a glowing red surface beneath the sky. WASP-76b is a giant gas planet, and there is no evidence of a clearly defined solid surface where anyone could stand. That temperature belongs to the atmospheric layers through which light can pass, or from which thermal radiation escapes into space. Deeper down, the gas becomes denser, the pressure rises, and the physical conditions change dramatically. There may be no simple boundary where the sky ends and the ground begins. The upper atmosphere is only the thinnest part of a much deeper and heavier world, where matter may enter states that are difficult to imagine through ordinary experience. The night side of WASP-76b receives no direct starlight, but it does not become an icy region. Its thick atmosphere and powerful winds carry enormous amounts of heat from the illuminated side. Temperatures there may still exceed 1,000 degrees Celsius, far hotter than any natural place on Earth's surface. The difference becomes meaningful only when the two hemispheres are compared. The day side is hot enough for many metals to become vapor, while the night side is cool enough for some of that vapor to begin condensing. The darkness does not need to become cold in the way we understand cold. A decrease of only a few hundred degrees may determine whether iron continues drifting through the atmosphere or gathers into tiny particles. Between these two regions lies a twilight belt encircling the planet. Seen from space, it might resemble the dividing line between the illuminated side and the dark side. But this boundary is not a thin line, nor does it remain still like ink drawn across a map. It is a broad region where the light gradually fades, the temperature changes, and the atmosphere continually flows through. On one side of this belt, gas has just left the day side and is entering darkness. It still carries a great deal of heat, along with metal atoms that remain in vapor form. Farther along, the gas begins to cool, creating conditions in which cloud particles may form. On the opposite side, matter that has traveled through the long night is returning to the region of intense light. The two edges of the planet are therefore not the same, even though both lie between day and night. One edge carries the signature of the dayside furnace. The other contains gas that has already cooled, where some of the iron may have condensed and left the upper atmospheric layers. This difference is one of the most important clues astronomers use when tracing the possibility of iron rain. The twilight belt is not completely calm either. Clouds may thicken and then disappear, while currents at different altitudes move at different speeds and in different directions. An upper layer may race around the planet, while a deeper layer responds more slowly. The atmosphere resembles a river with many levels, each carrying its own share of heat and material. This motion means that the hottest region does not necessarily lie directly beneath the point where the star shines most intensely. If the atmosphere were still, the area receiving the strongest direct light would probably also be the hottest. But winds can carry hot gas sideways before it releases all its energy, shifting the hottest point away from its original position. Astronomers detect this shift by following the planet's brightness throughout an entire orbit. When the hottest region turns toward Earth, the amount of thermal radiation we receive increases. If the brightest moment arrives earlier or later than expected, it suggests that heat has been transported away from the place directly beneath the star. Clouds make the picture even more complex. A hot region may release more thermal radiation, while an area covered by bright clouds may reflect starlight more effectively. These two sources of brightness do not have to be concentrated in the same place. The brightest point on the planet's map is therefore not necessarily the hottest. Even the boundary between day and night may change with altitude. In the upper atmosphere, light arrives at a different angle than it does in deeper layers. A thick cloud may extend darkness farther, while transparent gas allows light to penetrate beyond the geometric boundary. Twilight on WASP-76b is therefore a region with depth, not a simple flat line. If it were possible to drift through this area, the scene would change much more slowly than a sunset on Earth. The star would not truly sink because the planet was turning beneath the observer. Instead, winds would carry gas and clouds across an almost fixed boundary. The material itself would move from light into darkness, while the position of twilight remained wrapped around the planet. An iron atom might begin its journey in the hot atmosphere of the dayside. Carried by the wind, it would gradually leave the region receiving the strongest light and enter the twilight belt. The temperature would fall little by little. When the conditions became suitable, that atom might join with others, becoming a tiny particle or part of a forming droplet of metal. On the opposite side, particles that have passed through the darkness may be carried back into the light. As the temperature rises, they evaporate, releasing iron into the atmosphere once again. This creates a vast cycle, not entirely like Earth's water cycle, but still driven by temperature changes between the two hemispheres. One half of the planet continually turns material into vapor, while the other creates conditions for it to condense. Yet the two regions do not behave like sealed rooms. The atmosphere constantly mixes them, carrying heat into darkness and returning matter to the light. It is this circulation that keeps the entire system alive. Without winds, the day side could become much hotter, while the night side would lose heat more quickly. The contrast would then grow even more extreme. But the atmosphere partially softens the difference by transporting energy around the planet. It cannot erase the divide, but it prevents the dark side from becoming a completely separate world of cold. These atmospheric currents can reach tremendous speeds because the temperature difference is constantly maintained. The day side is heated without pause, while the night side continually releases heat into space, preventing the atmosphere from ever reaching a calm equilibrium. It is always trying to redistribute energy, like an enormous weather system that has never stopped moving since the planet became tidally locked. Near the equator, a powerful current may sweep material around the entire world. Closer to the poles, the motion may become more complex, with swirling regions or streams of gas moving in different directions. The upper layers respond quickly to starlight, while deeper layers retain heat for much longer. The entire atmosphere is a layered system in which no single wind direction can explain every movement. We cannot send a probe there to release weather balloons or measure the winds directly. The picture we have today is assembled from light, temperature, and climate models. Each model must explain several signals at once, from the location of the hottest region to where iron vapor appears, as well as the differences between the planet's two edges. When the data do not match, the model must change. If iron vapor is predicted along the morning edge, but the telescope does not detect it, scientists must consider whether the iron has condensed or sunk into deeper layers. If the brightest region appears somewhere other than expected, the way the atmosphere transports heat or distributes clouds must also be revised. Every small deviation in the light becomes a doorway into the climate of WASP-76b. A faint signal may reveal the direction in which winds are carrying hot gas. A missing portion of the spectrum may expose the presence of metals. A region that reflects more strongly may hint at clouds forming near the boundary between day and night. Tidal locking created the foundation for all of these phenomena. If WASP-76b rotated quickly like Earth, each region of the atmosphere would pass through light and darkness in turn. Heat would be distributed over time, and the contrast between the two sides could not remain so strong for long. Here, however, the same half of the planet continuously receives energy, dividing the climate into more persistent regions. The day side acts as a source of heat and metal vapor. The night side becomes a place where material cools, condenses, and sinks. The twilight belt forms the bridge between them, where the state of the atmosphere begins to change. The entire planet operates like a weather machine, driven by a motionless source of light in one half of the sky. Within this division, no region truly exists on its own. The darkness still receives heat from the day side, while the illuminated region continually receives material returning from its journey through the night. Clouds born in one place may disappear in another. Iron vapor rises, drifts away, condenses, and may eventually evaporate once again. Perhaps it is near the day-night boundary that tiny droplets of metal are forming within the clouds. They may survive long enough to reflect some of the star's light, or quickly fall into deeper layers before the winds can carry them back. We have never seen this process directly, but the changing light shows that the material in the atmosphere is never still. One half of WASP-76b never sees night, while the other never welcomes dawn. Even so, the atmosphere continually crosses that seemingly fixed boundary, carrying heat, clouds, and metals around the entire planet. This unending flow is what turns a divided world into a single connected system. There are no oceans to store heat, no continents to guide the winds, and no clearly defined ground where rain can fall. Yet WASP-76b still has weather, and that weather is powerful enough to carry materials as heavy as iron from the bright side into the darkness. To understand how metal rain might begin, we need to leave the day-night boundary behind and move deeper into the shifting layers of the atmosphere. Because on this world without seas, wind, clouds, and rain still exist, but in forms entirely unlike anything familiar on Earth. Leaving the day-night boundary behind, we can move deeper into the layers of gas, carrying metals around WASP-76b. On this world, there are no coastlines for winds to cross, no plains waiting for rain, and no clearly defined surface marking where the atmosphere ends. There are only vast layers of gas, one beneath another, growing denser, hotter, and more highly pressurized with depth. Imagine drifting within that atmosphere, standing on nothing and unable to look down toward any land below. All around us, currents of gas are constantly moving, with each layer carrying a slightly different temperature and composition. The upper regions respond quickly to starlight, while deeper layers retain heat for longer, move more slowly, and remain almost entirely beyond the reach of our telescopes. On Earth, when we think of weather, we usually think of water. Water vapor rises from the oceans, condenses into clouds, and returns to the ground as rain. The seas supply moisture, continents redirect the winds, and mountains and valleys create different climates. For that reason, it is easy to imagine that a planet without oceans cannot have weather either. But oceans are not required for wind, clouds, or rain to exist. As long as one region receives more energy than another, the atmosphere has a reason to begin moving. And if the atmosphere contains materials that can change from vapor into droplets and then back into vapor again, a weather system can still form in a way unique to that world. On WASP-76b, this imbalance reaches an extreme. One half of the planet receives constant starlight, while the other receives no direct illumination at all. The heat entering the day side cannot remain in one place. Hot gas expands, becomes lighter, and begins to move, while cooler regions create a contrast strong enough to set the entire atmosphere in motion. In the darkness, the heat carried in by the winds does not remain forever. The night side faces open space and continually releases energy as radiation. One side is heated without pause, while the other is always tending to cool. The difference between these two states never disappears, keeping the atmosphere in constant motion and preventing it from settling into lasting stillness. From a distance, that movement might resemble an enormous curtain being drawn across the twilight boundary. The part of the curtain that has just left the day side still carries heat and materials that have evaporated. As it moves farther into darkness, it gradually cools, changes in composition, and blends with other currents continuing their journey around the planet. This curtain does not move evenly in a single direction. Upper layers may race around the equator like a broad band of wind wrapped around the entire world. At other altitudes, gas may flow toward the poles, sink into deeper regions, or rise again, creating a network of motion far more complex than a single wind blowing directly from day to night. Some currents cross the boundary between light and darkness quickly, carrying heat with them before they have time to cool significantly. Others descend into deeper layers, where pressure is greater and energy remains trapped for longer. When those currents rise elsewhere, the stored heat may be released, making local temperatures very different from what we would predict from direct starlight alone. Because the atmosphere is always moving, the heat map of WASP-76b does not resemble a simple bright circle centered directly beneath the star. The hottest region may be shifted to one side, while the night side receives more heat than expected. The contrast between the two hemispheres remains, but atmospheric currents continually stretch and distort the boundary between them. Heat is not the only thing carried along this journey. Light elements such as hydrogen and helium make up most of the atmosphere, forming the broad foundation of this giant gas planet. Mixed among them are less abundant materials, including metal atoms and molecules that can survive at different temperatures. Iron makes up only a tiny fraction of the entire atmosphere. Saying that WASP-76b may have iron rain does not mean that its sky is made entirely of metal. Just as water rain on Earth does not mean that our air consists only of water vapor. Most of the atmosphere is still composed of lighter elements. Iron stands out because it leaves a distinctive signature in the light that telescopes can detect. Even a very small amount of iron can produce clear absorption lines if the light passes through a sufficiently long stretch of atmosphere. Each time the planet crosses in front of its star, starlight travels through the thin atmospheric rim before continuing toward Earth. The iron signal appears not because iron dominates the sky, but because its atoms absorb very specific colors of light. On the day side, intense heat allows iron to remain in vapor form within the atmospheric layers we can observe. Those atoms drift among other components and are swept into currents moving toward twilight. They do not form a separate river of metal, but remain mixed throughout the vast atmosphere. Much like invisible water vapor can exist within the air before becoming a cloud. As the gas approaches the dark side, the temperature falls. Iron does not instantly become large droplets the moment the light disappears. The atoms must first meet, join into tiny clusters, and then gradually grow into larger particles. These particles may become cloud seeds, gathering more material from their surroundings until they are heavy enough to fall. The process is very different from familiar rain, yet the sequence of change is not entirely unfamiliar. Water vapor in Earth's atmosphere does not suddenly become a large raindrop. It first collects around tiny particles of dust or salt, forming countless small droplets within a cloud. These droplets collide, combine, and eventually grow large enough to fall. On WASP-76b, the materials and temperatures are completely different, but the story may follow a similar rhythm. Metal vapor cools, forms small particles, gathers into clouds, and then sinks under gravity. The droplets may survive only briefly before entering a hotter region, breaking apart, or evaporating once again. Not every droplet falls in the same direction or reaches the same depth. Some may remain suspended in the upper atmosphere, held aloft by powerful winds, and carried great distances before sinking. Others may grow more quickly, fall through the gas, and disappear from the region that starlight can penetrate. Once they reach sufficient depth, pressure and temperature may transform them further in ways we cannot yet observe. Here, rain does not need to reach the ground in order to be called rain. A droplet of material only needs to form within the atmosphere and fall into a lower layer. It may never reach a core or any solid boundary at all. Its journey ends when it evaporates, blends into deeper material, or simply leaves the portion of the atmosphere visible to telescopes. If a droplet of water were released high in Jupiter's atmosphere, it would also be unlikely to fall onto a surface resembling Earth's. Along the way, changing temperature and pressure would carry it through several different states before it reached the deeper layers. WASP-76b may behave in much the same way, except that the condensing material may be metal rather than water. Viewed this way, iron rain begins to feel less like a scene from science fiction. It does not require a glowing red sky above a sea of molten ground. It requires only iron vapor in the atmosphere, a region cool enough for that iron to condense, and gravity to pull the droplets downward. All three conditions may exist within the planet's enormous atmosphere. Iron clouds, if they exist, are also unlikely to cover the entire night side evenly. Temperature depends on altitude, location, and the speed of atmospheric currents. An upper layer may cool quickly as it radiates energy into space, while a lower layer retains too much heat for iron to condense. Clouds may form only within a narrow range of altitudes where conditions are suitable for small droplets to survive. Even a passing current of hot gas could shift the cloud boundary. Newly formed particles might evaporate again, while a cooler region could cause the cloud layer to thicken. The nightside weather may not be a steady rain falling across the entire hemisphere, but a constantly changing system in which clouds form, drift, and disappear. We do not yet know how dense those clouds may be. They could be only a thin layer of particles, enough to alter the light without producing heavy rainfall. It is also possible that in some regions, condensation becomes strong enough for droplets to fall continuously. At present, the observations show only that iron may be leaving its vapor state as it enters the dark side. The clearest clue lies in the absence of iron vapor along one edge of the planet. Gas enters the night side, carrying a fairly strong iron signature. But when it reappears at the opposite edge, the amount of iron vapor in the observable layers has decreased. Something has happened in the darkness, preventing the iron from continuing to drift at the same altitude as before. Condensation is the most fitting explanation, because the temperature falls in exactly the way required. Iron atoms gather into droplets, become heavier, and sink downward, leaving the layer of gas through which the starlight passes. The telescope does not see the falling itself, but it detects the result left behind: less iron vapor when the gas returns to the illuminated side. This method of observation can be imagined as standing outside a sealed room. We see water vapor entering through one opening, but when the air emerges from the other side, the amount of vapor has decreased, even without seeing inside. That change allows us to infer that some of the water has condensed on cooler surfaces. On WASP-76b, the room is an entire hemisphere immersed in darkness. During the journey across the night side, iron may not be the only component to change. Many other metals and compounds have their own condensation temperatures. Some may form clouds before iron does. Some may appear only in deeper layers, while others may remain in vapor form throughout the entire journey around the planet. The atmosphere may contain several cloud layers stacked one above another, each made from a different kind of material. Seen from within, those clouds would probably not resemble water clouds in color. Metal or mineral particles absorb and reflect light in their own ways, making atmospheric layers appear brighter, darker, or differently colored depending on the wavelength. To telescopes on Earth, those differences show up only as tiny changes in the planet's brightness and spectrum. Clouds may also hide the materials beneath them. When particles form a layer thick enough, light can no longer penetrate to the same depth, causing the signatures of certain atoms to weaken. So the disappearance of iron from the spectrum does not necessarily mean that all of it has fallen away. Some may simply be concealed behind newly formed clouds. No signal from an atmosphere carries only one possible explanation. Temperature, clouds, winds, and chemistry are constantly affecting one another. A small change in light may come from several different processes, so scientists must test each possibility and determine which model can explain all the data without creating new contradictions. In many models, a powerful current flowing around the equator plays an important role. It carries heat from the day side to the night side, while shifting the hottest region away from the point directly beneath the star. That current may continue around the planet, returning the remaining material to the illuminated side before another cycle begins. Near the poles, the gas may follow different paths. Some of it may leave the hot region, move into darkness, then converge and sink, before returning to the day side through deeper layers. Rising and descending currents form vast circulation cells, somewhat like those in Earth's atmosphere, but broader, hotter, and shaped by entirely different rotational forces. There are no mountains or continents to redirect the winds, yet the atmosphere still creates structure through other forces. Rotation rate, gravity, temperature differences, and atmospheric depth all influence the way the currents move. Even a world without solid ground can develop wind bands, swirling regions, and long-lived areas where clouds gather. In the upper layers, stellar radiation acts quickly and intensely, causing the temperature to change sharply as gas crosses the boundary between light and darkness. Deeper layers respond more slowly because they contain more material and retain heat for longer. This difference causes atmospheric layers to slide past one another, sometimes in the same direction and sometimes at an angle, creating wind shear that may break clouds apart or build them again. A newly formed metal cloud may be stretched into a long band. Small droplets follow the current, while larger ones begin to sink. If wind direction changes with altitude, the cloud can separate into several layers, causing its shape to change continually even while its general location remains near the twilight region. This constant disturbance is what makes the possibility of a glory so remarkable. To produce clear rings of light, cloud particles need to be relatively similar in size and remain stable for long enough. A turbulent atmosphere would seem poorly suited to that, yet the unusual light signal suggests that one cloud region may be more stable than the rest. Perhaps droplets are continually forming at nearly the same size as iron vapor crosses a particular temperature threshold. A current may also keep them confined within the same atmospheric layer, preventing them from mixing too quickly with surrounding regions. These possibilities are still being considered, because no one yet knows what material truly creates the reflective area. Whether or not the glory is eventually confirmed, WASP-76b still shows that weather does not belong only to planets with oceans. It appears anywhere energy is distributed unevenly, gas is free to move, and matter has the chance to change state. On Earth, that story is written in water. Here, it may be written in iron and other metals. A planet without seas but with rain sounds like a paradox, only because we are so accustomed to thinking of water as the center of every weather system. Elsewhere, clouds can be made from completely different substances. Some worlds have hydrocarbon rain, others have acid clouds, and on still hotter planets, minerals may condense within the atmosphere. WASP-76b pushes that idea to a striking extreme. The material used to build tools and structures on Earth may become vapor, cloud, and rain on another world. Something heavy, solid, and familiar becomes part of an atmospheric cycle, simply because the temperature and pressure have moved far beyond anything we know. The atmosphere connects the entire process. It takes metal vapor from the hot side, carries it through twilight, and delivers it into darkness, where temperatures allow droplets to form. Whatever has not fallen may continue around the planet, return to the day side, and evaporate once again beneath the stars' intense light. No river flows between the two halves of the planet, but the atmospheric currents perform a similar role. They transport energy and material, linking the place where iron rises with the place where iron may fall. In this way, the day side and night side are not two separate worlds, but two stages within the same weather system. Each atom within that system may undergo a very long journey. It appears in the hot gas, is swept across the boundary between light and darkness, meets other atoms, and sinks as part of a tiny particle. Later, it may remain in deeper layers or be carried upward again to continue the cycle. No one knows how long a complete cycle might take. It could last only a few Earth days, or much longer, if the material falls deep into the atmosphere. Even so, each signal in the light suggests that this exchange is truly taking place, strongly enough for an element to appear along one edge and nearly vanish along the other. The winds of WASP-76b carry more than heat. They sweep along tiny pieces of the planet itself, atoms once locked inside matter, and then released into the atmosphere by intense temperatures. Every current crossing the twilight region may carry a different chemical story, depending on where it began and the path it has taken. When we speak of weather on WASP-76b, we are not speaking only of powerful winds or strange clouds. This is a system capable of carrying metals around an entire world, changing them from vapor into droplets, and perhaps returning them to vapor again. The rain is only one moment within a much larger cycle. At the boundary between day and night, the atmospheric curtain continues drifting into darkness. Within that moving gas, an iron atom slowly leaves behind the place where it was once heated. Only a short distance earlier, it was still moving freely as vapor, mixed among streams of hot wind. Ahead, the starlight fades and then disappears completely. The temperature falls just enough for atoms to begin coming together. On a world without seas, metal is preparing to enter a cycle of its own. Within the current crossing the twilight, iron begins to cool, gather, and become part of the weather. Within the current of gas drifting through the twilight region, That iron atom gradually moves away from the place where it was once heated. Starlight still illuminates the layers of atmosphere behind it, but ahead, the darkness has already begun to stretch farther. The temperature falls with every distance it travels, beginning a transformation that, on Earth, we rarely imagine iron could ever undergo. In our world, iron usually feels heavy, solid, and resistant to change. It lies within rocks deep beneath the ground and appears in buildings, ships, and familiar everyday objects. To turn iron into vapor, humans must create temperatures so extreme that very few places on Earth can sustain them for long. WASP-76b needs no separate furnace. The atmosphere permanently facing the star has become one vast heated region where temperatures may rise above about 2,400 degrees Celsius. In such an environment, many molecules can no longer preserve their familiar structures, while elements normally locked inside rock may appear in the atmosphere as free atoms. The entire planet is not becoming an ocean of vaporized iron. Most of the atmosphere is still made of light gases, forming the broad gaseous envelope typical of giant planets. Iron accounts for only a small fraction, yet each of its atoms can absorb very specific colors of light, allowing telescopes to detect it from hundreds of light years away. An iron atom suspended in the atmosphere does not resemble a tiny piece of metal flying through the air. It no longer belongs to an iron bar, a rock, or any other solid object. Within the hot gas, it moves freely among countless other atoms, colliding constantly before being swept into winds, flowing away from the region receiving the strongest starlight. The heat has released it from its familiar state, and the atmosphere now determines where it will travel. The atom blends into the current like a drop of ink dissolving in water, never forming a separate cloud of iron vapor that could be seen directly. It is only a tiny component within the enormous atmospheric curtain being drawn from the day side toward the darkness. The motion of gas on WASP-76b may be far faster than anything we associate with ordinary winds on Earth. The spectral signature of iron has been measured with a shift of about 11 kilometers per second, although that figure combines the planet's rotation with winds blowing away from the day side. Other studies have also found day-to-night flows ranging from several to nearly 10 kilometers per second, equivalent to tens of thousands of kilometers per hour. These numbers do not mean that every atmospheric layer moves at the same speed. Some layers may race around the equator. Others may descend into deeper regions, while still others may swirl or bend toward the poles. The iron atom we are following travels along only one of the many possible paths through this vast atmosphere. As it approaches the twilight region, it remains within gas hot enough to preserve its vapor state. Starlight begins to pass through the atmosphere at a lower angle, gradually weakening the direct source of heat. Yet the current still carries energy absorbed on the day side, so the gas does not cool instantly when it crosses the boundary between light and darkness. Twilight on WASP-76b is not like the brief moment when the sun slips behind Earth's horizon. It is a broad region through which matter continually flows, while the boundary of light remains almost fixed. Gas, clouds, and atoms are the things in motion, while the day-night divide circles the planet like a doorway, permanently open toward the dark. The iron atom passes through that doorway with the current. Behind it, other layers of gas are still being heated until metals can become vapor. Ahead lies a cooler region, although it remains far hotter than any rainstorm that has ever existed on Earth. Iron does not have a single condensation temperature that applies everywhere. The threshold changes with pressure, atmospheric composition, and altitude, much as water boils at different temperatures when the pressure changes. There is no invisible line where every iron atom suddenly becomes a droplet at the same moment. The transformation begins more quietly. When the gas cools enough, iron atoms may meet and form extremely small clusters. At first, these clusters are tiny enough to remain suspended and move with the gas as though they were still part of it. They may then continue gathering material if the surrounding conditions allow. Small mineral particles may already exist in the atmosphere, providing surfaces for iron to collect upon. It is also possible that iron clusters form on their own when enough atoms gather in the same region. We do not yet know which process plays the greater role on WASP-76b, because telescopes currently see only the combined signatures of gas, clouds, and light. As the particles grow, they no longer respond to the atmospheric flow in quite the same way as individual atoms. Gravity begins pulling them toward lower layers, while the winds continue trying to carry them sideways around the planet. The journey of each particle becomes a gentle struggle between drifting with the atmosphere and sinking toward denser gas below. If the particles continue to merge or gather more iron, they may become small droplets. Under some of the temperatures and pressures predicted for WASP-76b, liquid iron is a plausible form for the condensed material. Even so, the phrase iron droplets remains a description based on models, not an object that any telescope has directly photographed. Those droplets may be as fine as mist, or they may grow larger if they survive long enough within a dense cloud layer. No one yet knows their true size, because the available light signals cannot reveal the width of individual droplets. The image of iron rain therefore still contains many unknowns, built from what we understand about temperature, pressure, and the way iron changes state. Rain does not need to reach the ground in order to be called rain. Matter only needs to condense within an atmosphere, become heavier, and fall into a lower layer. On WASP-76b, where no clearly defined solid surface has been found to mark the end of the journey, rainfall may take place entirely between layers of gas. A falling iron droplet would enter regions of increasing pressure. The temperature would not necessarily continue to decrease with depth, because the interior of the planet may grow hotter again. The droplet could evaporate before traveling very far, blend into another layer of gas, or continue sinking until it disappears beyond the part of the atmosphere that starlight can penetrate. There would be no sound of metal striking the ground, and no molten lake waiting below to receive the falling drops. A more realistic scene would be a cloud layer suspended in darkness, where countless tiny particles appear, grow, and then fall out of the gas that holds them. The rain would end within the atmosphere itself, requiring no surface below to complete its journey. Within the lasting darkness, those tiny droplets would probably not glow like sparks. They would receive only weakened light from the planet's edge or reflect thermal radiation from the surrounding gas. After a brief time within the cloud, they would quietly sink into deeper regions, carrying iron away from the atmospheric layers our telescopes can observe. That disappearance is the most important clue of all. Astronomers do not need to see each droplet fall in order to recognize that the iron has changed. They only need to compare the amount of iron vapor present before the gas enters the darkness with the amount that remains after it crosses the night side and returns to the illuminated region. In observations made with the espresso instrument on ESO's Very Large Telescope, the signature of neutral iron appeared more clearly along the evening boundary, where gas was leaving the day side. Near the morning boundary, the same signal did not appear in the same way, leading the research team in 2020 to conclude that iron may have condensed during its journey across the night side. Imagine a current of gas entering the darkness while iron is still drifting freely within it. After crossing half the planet, that same current emerges again, but some of the iron is no longer present at its original altitude. It may now be locked inside cloud particles, have fallen into deeper layers, or be hidden behind material that light cannot easily penetrate. The gap in the signal is what gives rise to the image of iron rain. It is like watching a line of vehicles enter a tunnel, and then noticing that some of them never appear at the other end. We cannot see what happens inside the tunnel, but the difference between what enters and what comes out tells us that something occurred in the darkness between. Condensation is an appealing explanation because it fits the planet's temperature pattern. The day side is hot enough for iron to remain in the gas, while the night side is considerably cooler. Winds connect the two regions, creating a natural journey from evaporation to cooling, and from cooling to particle formation. Even so, the story is not completely settled. Atmospheric models developed after the original discovery showed that the difference in the iron signal may also be influenced by temperature contrasts between the two edges, obscuring cloud layers, and the way winds shift the light. Some models cannot explain the entire signal through iron condensation alone, but fit the data better when high-altitude clouds are included. Those clouds may contain iron, magnesium-rich minerals, or other heat-resistant materials. They may hide the gas behind them, making iron vapor appear to vanish even when some of it is still present. The lower temperature along the morning edge may also weaken the iron signal, even if the actual amount of iron has not fallen as much as the first explanation suggested. For that reason, the phrase iron rain should be understood as a well-supported scientific hypothesis, not as a scene that has been directly confirmed. The data show that the atmosphere is different along the two edges, and that iron may be changing state in the darkness. What remains uncertain is how much iron truly condenses, what shape the particles take, and how much the clouds contribute to the signal we receive. That caution does not make the planet any less strange. Instead, it suggests that the weather on WASP-76b is richer than a simple atmospheric cycle. Iron may be condensing while also being hidden by clouds, as winds and temperature differences work together to create the picture seen by telescopes. An iron atom does not necessarily have only one possible fate. Some atoms may join into droplets and fall, while others remain as vapor and continue around the planet. Some particles may stay suspended within clouds for many hours, while others sink into deeper layers or evaporate when they encounter a hotter current. If deep atmospheric flows carry the material back toward the day side, the cycle may begin again. Iron trapped inside a particle or droplet encounters rising temperatures, separates, and returns to vapor. The winds then carry it through the twilight region once more, toward the place where new particles may form. This cycle brings to mind the movement of water on Earth. Although the two stories are not identical, our water rises mainly from oceans and returns to a clearly defined surface, while iron on WASP-76b may change state entirely within the atmosphere. There is no iron sea supplying the vapor, and we do not yet know how deep the falling droplets ultimately travel. The most important similarity is simply the change of state. Heat carries material into the gas. Cooling allows it to gather, while gravity pulls the heavier particles downward. If atmospheric currents return that material to the hotter region, it has another chance to become vapor and begin a new cycle. Iron is probably not the only element taking part in this kind of weather. The spectrum of WASP-76b has revealed signs of several other metals, including magnesium, chromium, manganese, and nickel. Each element may condense at a different temperature and altitude, allowing the atmosphere to contain several cloud layers with different compositions. One cloud layer may form as soon as the gas begins to cool. Another may appear only after the current travels deeper into the night side. These layers may overlap, reflect different colors, or hide the elements beneath them, creating a sky far more complex than one made from iron clouds alone. Much of what we call iron rain may occur only within a fairly narrow range of altitudes. Too high in the atmosphere, the gas may remain too hot or too thin for droplets to grow quickly. Too deep below, the temperature and pressure may change again, returning the iron to another state before its journey continues. These questions still have no clear answers. We do not know how far the droplets fall, how long they survive, or whether they ever grow to the size of familiar raindrops. No one has identified a separate iron cloud at a precise altitude, and we cannot yet say whether the material returns to the dayside quickly enough to create a steady repeating cycle. Telescopes view the atmosphere through only a very thin edge, much like trying to understand an entire house from the light escaping beneath a door. Most of what happens in the deeper layers remains hidden. Some iron may fall and remain there for a very long time, while another portion is carried back upward, and we cannot yet separate those two paths. Among these uncertainties, the basic picture remains consistent. The day side provides enough heat to place iron into the atmosphere. Winds carry it away from the hottest region, while the night side creates conditions in which the atoms can gather into particles and perhaps fall. The atmosphere becomes the bridge between those two states. Without moving gas, the iron would struggle to leave the hot region and reach a place where it could condense. Without the temperature difference, there would be no reason for it to change from vapor into droplets during its journey around the planet. Somewhere in the darkness of WASP-76b, a cloud layer may be forming even now, although the light we observe takes centuries to reach Earth. Tiny particles appear within the hot gas, grow, and begin to sink, producing no sound that could ever cross the space between the stars. They leave only an indirect trace in the light. Iron vapor appears where the gas enters the night side, then weakens as the current returns to the light. Within that delicate difference, the entire image of metal rain is built not from a photograph, but from the absence of atoms that should still have been there. Iron rain is therefore more than a dramatic name for a distant planet. It is a physical explanation that fits the temperature, the winds, and the asymmetry seen in the spectrum. That explanation must still be tested against new models and observations, but it has already transformed a very small signal into a story of weather on a world without seas. The iron atom we have followed may now have become part of a metallic droplet falling toward deeper atmospheric layers, or it may still be drifting within a cloud, waiting for the winds to carry it somewhere else. Whichever path it takes, it has left the place where it once existed as vapor and entered a completely new stage of its journey. Above, the twilight boundary continues receiving fresh currents from the day side. Below, newly formed particles keep sinking into the darkness, where they may evaporate, remain, or eventually find a path back toward the light. The entire cycle unfolds quietly, driven by illumination on one side and cooling on the other. If iron truly condenses during this journey, its signature should change between the two edges of the planet. Iron vapor should appear as the gas leaves the day side, but after the long passage through darkness, that signal should weaken or disappear from the atmospheric layers we can observe. This is no longer only a prediction. The difference between evening and morning has been recorded in the star's light, revealing the clearest clue yet to a rainstorm that no telescope has ever seen directly. The clearest trace of a rainstorm no one has ever seen appears during the few hours when WASP-76b passes in front of its star. At that moment, the planet blocks part of the starlight, while a very small amount still slips through the gas surrounding its edge. The light then continues toward Earth, carrying the signatures of the atoms it encountered along the way. At first glance, the planet's edge is only a thin outline surrounding a dark sphere. But WASP-76b has two very different edges. One has just completed a long journey through darkness and is preparing to return to the light. The other has only recently left the furnace of the day side, still carrying heat and materials that have not yet had time to condense. We can imagine them as two doors at opposite ends of the same room. The evening door opens from the illuminated side into the night, where the flowing gas remains hot after spending hours under direct radiation from the star. The morning door lies at the other end, where the gas has crossed the entire night side before returning to the light. The gas entering through the first door does not necessarily resemble the gas emerging through the second. Within the darkness between them, the temperature has fallen, clouds may have formed, and some material may have sunk into deeper layers. Simply by comparing the light passing through these two doors, astronomers can begin to understand how the atmosphere changes during its journey around the planet. A transit begins when the leading edge of WASP-76b first touches the bright disk of the star. This is the morning edge, where gas has just completed its passage through the darkness and is returning to the light. During the opening minutes, Most of the planet still lies outside the stellar disk, so the light passing through this region carries more information about the edge entering first. As the planet moves farther across the star, the entire sphere gradually blocks part of its light. Starlight then passes through both sides of the atmosphere, causing their signatures to blend together. Near the end of the transit, the evening edge is the last part remaining in front of the star, allowing the telescope to detect more clearly the signal from gas that has just left the day side. Within only a few hours, the same telescope can look through two different regions of a world hundreds of light years away. No camera captures the clouds or winds along either edge, but the planet's motion naturally places each atmospheric region in front of the light source. The star becomes an enormous backlight, while WASP-76b slowly carries both of its edges across that distant glow. The crucial observations were made with espresso, an instrument capable of separating light into extremely detailed bands of color, mounted on ESO's very large telescope in the Atacama Desert. During its first scientific observation in September 2018, the instrument recorded the star's light throughout the planet's transit. The results later revealed a strong iron vapor signal along the evening edge, but not the same signature near the morning edge. Espresso does not see iron atoms as tiny points suspended in the atmosphere. It receives only a stream of light that has traveled from the star, passed through the planet's atmosphere, and continued onward to Earth. When that light is separated, a few very narrow colors appear weaker than those beside them, like a complete piece of music, with several small notes missing. Each element removes its own group of colors from the light. Iron leaves gaps different from those produced by sodium, magnesium, or calcium, allowing its signature to be recognized even when it is mixed with the far brighter light of the star. Astronomers do not need to see the atom itself to know that it once stood in the path of the light. Reading a spectrum is somewhat like recognizing that someone has crossed a stretch of sand, even after they are gone. The shape of the footprints reveals that someone passed through. The distance between the steps hints at their speed, and the direction of the trail shows where they were going. A spectrum preserves a similar story, except that these footprints are written in missing colors of light. The signature can also shift slightly when the gas is moving toward us or away from us. A familiar comparison is the way the pitch of a vehicle changes as it approaches and then recedes. With light, the change in color is far too small for the eye to notice, but a sensitive instrument can measure the shift and infer the motion of the gas. The iron signal on WASP-76b did not remain still throughout the transit. It gradually shifted farther toward the blue as the evening edge became more clearly visible. The 2020 research team measured a shift of about -11 kilometers per second in the atmosphere, trailing behind the planet, equivalent to nearly 40,000 kilometers per hour. This number should not be interpreted as a single wind blowing uniformly through the entire atmosphere. It contains the combined effects of the planet's rotation, its orbital motion, and atmospheric flows moving from the hot region toward the darkness. Even so, it shows that the iron-bearing gas is traveling at tremendous speed, fast enough to carry material across vast distances on the planet in a short time. At the evening edge, the gas has only recently left the hemisphere that permanently faces the star. It remains hot and expanded, rising higher above the planet than cooler gas. Iron vapor may continue to survive in these upper layers, where starlight can easily pass through it and leave a relatively clear absorption signature. The image of a doorway leading away from a furnace is especially fitting here. The gas flowing through it has not yet had much time to cool. Iron atoms are still drifting freely, and condensed clouds may not have formed thickly enough to hide the signal. As a result, the light encounters more iron vapor on its journey toward the telescope. The journey then continues deeper into the darkness. The gas no longer receives direct radiation and gradually releases its stored heat into space. The night side remains extremely hot by earthly standards, around 1,500 degrees Celsius in the original picture, but it is considerably cooler than the dayside, where temperatures may rise above 2,400 degrees Celsius. That difference is large enough to change the chemistry of the atmosphere. When conditions become suitable, some of the iron may begin gathering into tiny particles. These particles grow, become part of clouds, and then sink under gravity. By the time the gas reaches the morning door, the amount of neutral iron still drifting through the upper atmosphere may have fallen, leaving the light without the strong signature seen before. This is the explanation that created the famous image of iron rain. Iron is present when the gas leaves the dayside, but its signal weakens after the journey through the night side, consistent with the possibility that it has condensed and fallen into deeper layers. Astronomers do not see the rain itself, but they can see that some of the iron vapor has failed to return to the region that starlight can reach. Another research team later re-examined the phenomenon using data from HARPS, a different spectrograph. They combined 4 separate transits and still found the same asymmetry in the iron signal. The fact that the signature appeared in independent data helped rule out the possibility that the original result was merely noise, or a chance feature of a single night of observation. Even so, the phrase, "there is no iron in the morning," can create an image that is far too absolute. The telescopes did not prove that every iron atom had vanished from the entire morning edge. They showed only that neutral iron did not absorb light as strongly in the same way within the atmospheric layers the observations could reach. Some of the iron may have condensed into clouds, some may have sunk to lower altitudes, and some may still have been present but hidden behind cloud layers. The morning atmosphere is also cooler and more contracted, making the region capable of absorbing starlight thinner. A weak signal, therefore, does not necessarily mean that the actual amount of iron has fallen to zero. Imagine 2 layers of mist in front of the same lamp. The warmer mist may expand and rise higher, forcing the light to travel through a longer path. The cooler mist remains compressed below, so even if it contains a similar amount of material, it leaves a weaker signature because the light passes through only a thin layer. The 2 edges of WASP-76b may differ in much the same way. The evening edge is hotter, more expanded, and carries more iron into the altitudes visible to spectroscopy. The morning edge lies lower, may contain more clouds, and can obscure part of the gas beneath, causing the iron signal to become almost completely muted. 3-dimensional models have tried to recreate this exact change. Some show that the temperature difference between the 2 edges can make the iron signal appear asymmetric, even when the amount of iron does not differ greatly. Other models require an additional opaque cloud layer on the morning side to hide absorption that would otherwise be visible. Later analyses that separated the 2 edges still found iron to be more prominent on the evening side, while also showing that the atmosphere could not be accurately described as one uniform ring surrounding the planet. Temperatures in the observed regions may range from above 2,600 to nearly 3,000 Kelvin, while inferred day-to-night wind speeds range from about 6 to 10 kilometers per second, depending on the stage of the transit. These numbers do not make the story any simpler. They show that the iron signal is the result of several processes occurring together: hot gas expanding, the planet rotating, winds carrying material, clouds blocking light, and iron possibly condensing in the darkness. Each process contributes something to the final trace collected by the telescope. It is like seeing a person's shadow through a curtain moving in the wind. We can recognize the general shape, but we cannot immediately tell which part comes from the person behind it, which part comes from folds in the fabric, and which part is created by the direction of the light. To separate them, researchers must build many models, pass each possibility through the same observation, and see which story most closely matches the data. Iron rain remains a reasonable explanation because it fits the temperature and chemical changes between the 2 edges, but the more accurate picture is probably not one in which all the iron becomes rain the moment darkness begins. Some of it condenses, some continues to be carried by the wind, while temperature and clouds determine how much of it can actually be seen. That caution does not make the discovery any less remarkable. Before WASP-76b, astronomers often had to treat the entire edge of an exoplanet as a single atmospheric layer. This observation showed that the two sides of the same planet can leave different signatures during one transit. A world is no longer merely an average ring of atmosphere. It has a morning side shaped by its passage through darkness, an evening side still carrying the heat of the day, and winds connecting the two. By following how the signal changes from one stage to the next, human beings have begun to read the differences between regions on a planet that cannot be seen clearly. This is also why the original discovery was described as evidence of chemical change between day and night on an ultra-hot Jupiter. The atmosphere does not merely have different temperatures. Its materials may exist in different states depending on location. Iron drifts as vapor in one region, becomes cloud or droplets in another, and may return to vapor when it encounters intense heat again. A cycle that once existed only in models began to leave a trace in real data. The evening door shows iron entering the darkness. The morning door shows that after the journey, iron vapor is no longer strongly present at the same altitude. The missing part between those two doors is where clouds and rain may have formed. The darkness of WASP-76b is therefore not an empty region without activity. Even where the human eye would see no star, the atmosphere is changing from moment to moment. Heat is radiated into space. New particles appear, droplets of matter sink, and winds continue carrying gas toward a dawn that never truly rises. The story can be imagined through one final iron atom remaining high in the atmosphere. It enters the darkness with millions of others. But during the journey toward the morning edge, the atoms around it gradually gather into particles and fall. When starlight touches that layer of gas again, the chemical footprints have become more sparse. That atom may continue drifting, cross the morning edge, and return to the day side. As the temperature rises, the remaining particles evaporate, and the atmosphere begins another cycle. Not every atom follows the same path, but the overall difference among trillions of atoms is large enough to appear in the spectrum. Human beings detect that difference from an extraordinarily small amount of light. The star's light is far stronger than the atmospheric signal, while each iron line occupies only a narrow part of the spectrum. Astronomers must follow the entire transit and remove the effects of Earth's atmosphere, the motion of the star, and instrumental noise before the planetary signature can emerge. After all those steps, what remains is not an image of rain. It is a signal changing over time, weaker near the beginning and clearer toward the end of the transit. To the eye, it is only data. But when placed within the context of temperature, wind, and chemistry, that line becomes the trace of a journey through darkness. We cannot say exactly where each iron droplet forms or how far it falls. But the two edges show that the atmosphere does not return unchanged after crossing the night side. A real transformation has occurred, whether through condensation, cloud cover, contraction caused by lower temperatures, or some combination of all three. Evening has iron, morning does not, is therefore only a brief way of describing a much more complex picture. Along the evening edge, iron vapor appears clearly within the hot, expanded atmosphere. Near the morning edge, telescopes no longer see the same signal in the same way, showing that either the iron or the environment around it has changed during the journey through the night side. The two edges of the same planet are telling different parts of one cycle. The first carries metal from the dayside furnace into darkness. The second returns to the light with gas that has cooled, contracted, and may contain clouds formed from the same material that once drifted as vapor. This is the most important payoff in the search for iron. Metal rain is not suggested only by extreme temperatures or by our imagination of a distant world. It emerges as an explanation for a real asymmetry in the light, observed with multiple instruments and across several transits. Even so, spectroscopy tells us only which colors have been removed by the atmosphere. It can reveal iron, measure the motion of the winds, and compare the two edges, but it cannot directly show how a cloud region reflects light. To search for the glow resembling a rainbow, astronomers had to listen to the planet in a different way. Instead of looking only at the missing colors, as WASP-76b passed in front of its star, they followed the total light of the system throughout an entire orbit. As more of the day side turned toward Earth, the system brightened. When the night side faced us, the light declined. That rising and falling rhythm could reveal where heat was concentrated, where clouds appeared, and which regions reflected more starlight than expected. After using gaps in the light to find iron, we now turn to a completely different clue. A very small excess of light appearing precisely where WASP-76b crosses the boundary between day and night. After recognizing that iron appeared differently along the two edges of WASP-76b, astronomers were still missing an important part of the picture. The colors absorbed from the light could reveal what the atmosphere contained, but they could not show how the entire planet brightened and dimmed over the course of an orbit. To locate where clouds were concentrated, where heat had been shifted, and where part of the atmosphere reflected an unusual amount of light, researchers needed to follow the brightness of the whole star system continuously for many hours. WASP-76b is far too distant to appear as a clearly defined sphere. Its host star is vastly brighter than the planet, causing the faint light from WASP-76b to be almost completely overwhelmed. Through current telescopes, the two bodies still blend into a single point of light, like a distant lamp with a grain of dust beside it too small for the eye to separate. Even though we cannot see the planet itself, we can still detect the way it changes that point of light. Imagine a dark sphere moving around a lamp, with both so far away that they appear as a single dot. We cannot see markings on the sphere, or tell which side contains clouds, but the total brightness rises or falls depending on how much of the illuminated side is turned toward the observer. Over one orbit, WASP-76b gradually shows us its night side, part of its day side, almost the entire illuminated hemisphere, and then returns to darkness. The planet does not change shape. Only our viewing angle from Earth changes as it moves around the star. Each position along the orbit therefore resembles a different frame of the same world, although none is clear enough to become a true image. The observing cycle begins when WASP-76b passes in front of its star. At that moment, most of the hemisphere facing Earth is the night side, while the planet's body blocks a small amount of the light behind it. The brightness of the system drops for several hours, then rises again as the planet leaves the stellar disk. This event is called a transit, but to an observer, it is simply a small dip appearing in an otherwise nearly steady stream of light. The deeper the dip, the larger the portion of the star being blocked. By knowing the size of the star, astronomers can estimate the diameter of the planet without ever seeing its outline clearly. The way WASP-76b dims the light shows that it is an enormous world, with a radius nearly twice that of Jupiter. Even though its mass is slightly lower, the light passing close to the planet's edge carries another layer of information. A very small portion travels through the atmosphere before reaching Earth, where iron and other materials absorb certain colors. This is how the morning and evening edges told different stories in the previous chapter. A transit reveals both how large the planet is and opens a narrow window into the gas surrounding it. When WASP-76b moves away from the front of the star, the brightness of the system returns close to its original level. But the planet does not disappear from the story. It continues along its orbit, gradually revealing part of the illuminated day side. At first, only a narrow crescent is visible. Then more of the bright hemisphere turns toward Earth, causing the total amount of light we receive to increase little by little. The change is far too small to notice in a single glance. The star still provides almost all the light, while the planet contributes only a whisper beside a much louder sound. Telescopes must measure the brightness again and again, remain extremely stable, and identify tiny differences across thousands of consecutive observations. The light coming from the planet is a mixture of several components. Some is starlight reflected back into space by clouds or the atmosphere. Another portion is heat emitted by WASP-76b itself after being intensely warmed. At different wavelengths, the balance between these two sources changes, so each telescope may see a slightly different part of the same atmosphere. The planet's dayside can be imagined as a curtain that is both hot and reflective. Regions with higher temperatures may release more radiation, while areas covered by bright clouds may return more starlight. A region does not necessarily appear bright only because it is hot, nor only because of clouds. Sometimes both contribute to the signal. After about half an orbit, most of the dayside of WASP-76b faces Earth. The system is usually brighter than when the night side is turned toward us, because the telescope receives additional reflected light and heat from the planet. But just as that light is approaching its highest level, WASP-76b moves behind the star and is temporarily hidden from view. This moment is known as a secondary eclipse, or an occultation behind the star. Before the planet disappears, the telescope receives light from both the star and the planet. Once WASP-76b is hidden, only the star's light remains. The tiny drop between those two moments is the amount of light the planet had been contributing. This is an extremely delicate measurement. Astronomers cannot see WASP-76b separately, but the star briefly helps by covering it. By comparing the light before and during the eclipse, they can isolate the planet's contribution from the far brighter light of the host star, much like recognizing the sound of one instrument when it suddenly falls silent within an orchestra. If the missing light is greater than predicted, the dayside may be hotter or more reflective. If the decrease is weaker, the atmosphere may be darker, absorb more starlight, or release less heat at the wavelength being observed. Each time the planet passes behind the star, therefore becomes a measurement of its daytime face. WASP-76b takes only about 43 hours to complete a year, so its entire pattern of changing brightness can be observed within a relatively short time. The planet passes in front of the star. Its dayside gradually comes into view. The system brightens, and then it disappears behind the star. Afterward, WASP-76b emerges on the other side. The illuminated region slowly turns away, and the night side once again faces Earth. When all of these changes are placed together, they form a phase curve. The name may sound like a technical graph, but it is simply a record of the planet's brightness throughout one orbit. Each point on the curve shows how bright the system was at a particular moment, while the overall shape reveals how light is distributed between the dayside, the night side, and the regions between them. A perfectly regular phase curve would look fairly simple. The brightness would be lowest when the night side faced us, rise gradually as the day side came into view, reach a maximum near the moment the planet passed behind the star, and then decline through the remaining half of the orbit. But real atmospheres rarely distribute heat and clouds with perfect symmetry. If the hottest region lay exactly at the center of the dayside, thermal brightness would peak near the moment when the fully illuminated face was turned toward Earth. Strong winds can carry hot gas to one side, causing the peak to arrive earlier or later. Simply by observing when the curve reaches its highest point, astronomers can begin to infer the direction in which the atmosphere is transporting heat. The image is a little like a blanket being heated at one point, then pulled sideways by the wind so that the warmest region shifts away from the heat source. From a distance, the observer cannot see the wind itself, but can recognize that the hottest area no longer lies directly beneath the source of energy. On WASP-76b, the displacement of the brightness peak becomes one of the signs that the atmosphere is transporting energy around the planet. Clouds leave their own signature as well. One edge containing more reflective particles may appear brighter than the other, even if it is not hotter. If clouds gather near the morning side, the phase curve may rise as that region turns toward Earth. If those clouds disappear under the heat of the dayside, The reflected light may decrease even while the thermal radiation from the atmosphere grows stronger. No single measurement can immediately reveal whether the brightness comes from heat or clouds. Researchers must compare observations across several wavelengths of light. Visible light is usually more sensitive to reflection, while infrared observations reveal more clearly the heat emitted by the planet. When several telescopes observe the same world, each instrument contributes a different piece of the map. CHEOPS was designed to measure the brightness of stars already known to host planets with extremely high precision. It does not capture detailed images of WASP-76b, but continually monitors how the amount of light changes. A small but stable telescope in space can detect variations that are difficult to measure from the ground, where Earth's atmosphere constantly makes light shimmer and distort. For a planet with an orbit as short as that of WASP-76b, CHEOPS can follow many different parts of the brightness pattern within only a few days. Its measurements were combined with data from TESS, Hubble, and Spitzer, creating a broader picture of the day side, the night side, and the two boundaries between them. Each instrument observes a different range of wavelengths, helping researchers separate reflected starlight from heat emitted by the atmosphere. The resulting map does not resemble a weather map with clear coastlines and cloud formations. It is closer to a band of brightness wrapped around the planet, showing which regions appear lighter or darker as they turn toward Earth. Astronomers can estimate how brightness changes with longitude, but smaller details and motion near the poles remain difficult to isolate. Even in this rough form, the map is enough to distinguish a symmetrical world from a planet whose climate is shifted toward one side. It shows whether the brightest region lies before or after the center of the day side, how much heat the night side releases, and whether one edge reflects more light than the other. A sphere that cannot be seen directly begins to reveal its structure through the rhythm of its brightness. The process can be compared to looking into a room through frosted glass. We cannot make out individual objects, but if a lamp is carried from one side of the room to the other, the bright region on the glass moves with it. If a mirror lies near one wall, the light may suddenly intensify at a particular angle. We cannot see the mirror itself, but we can still tell that this part of the room reflects light differently from the rest. The phase curve of WASP-76b contains changes like these. A gradual rise may reflect the day side slowly turning toward us. A displaced peak reveals that winds have carried heat away from its expected location. A section that brightens more quickly than normal may suggest a region reflecting light in a very different way from its surroundings. The greatest challenge is that the star itself is not perfectly quiet. Dark regions, bright areas, and small fluctuations on its surface can cause its brightness to change. The instrument is also affected by temperature, spacecraft position, and background light. To isolate the planet's contribution, scientists must understand and remove as much of this unrelated variation as possible. A single observation is rarely enough to confirm a very small rise in brightness. If the signal appears during one orbit and disappears during the next, it may simply be noise or a fluctuation from the star. Only when the same feature repeats across several observations at the same orbital position does the possibility that it truly comes from the planet become more convincing. That is why CHEOPS did not observe WASP-76b only once before moving it on to another target. The satellite returned to the system across multiple observing sessions, recording the planet as it passed in front of the star, disappeared behind it, and moved through the orbital regions in between. Each return reduced the noise in the phase curve, like a blurred image, becoming clearer as more layers of data are placed on top of one another. Over 3 years, CHEOPS carried out 23 detailed observations of WASP-76b. The measurements showed that one boundary of the planet was unexpectedly brighter, beyond what could be explained simply by the day side, gradually turning toward Earth. The increase appeared rather quickly in the eastern region, near the place where darkness transitions into light on the planet's map. To recognize that this brightness was unusual, The research team first had to construct the planet's expected pattern. They calculated how a world as hot as WASP-76b should emit heat, how much starlight its day side might reflect, and how the brightness should change as the viewing angle shifted. The data were then compared with that predicted picture to find the places where the two did not match. Most of the phase curve followed a rhythm that could be understood. The brightness increased as more of the day side came into view, disappeared when the planet passed behind the star, and declined as the night side turned back toward us. But near one boundary, the data bent away from the smooth curve, like a note suddenly rising above an otherwise even melody. The difference was extremely faint. There was no moment when the telescope saw the planet flare, and no colored ring appeared clearly in an image. There was only a tiny excess of light, arriving at the exact moment when that region turned toward the observer. Yet the location and shape of the signal made it difficult to explain through ordinary temperature patterns alone. If the region were simply hotter, the light would be expected to change more gradually as it came into view. A cloud layer reflecting light equally in all directions would also tend to produce a broader rise in the curve. Instead, the signal appeared concentrated within a narrow viewing angle, as though the light were being directed more strongly toward Earth, only when the star, planet, and telescope entered a particular alignment. By this point, the distant point of light had revealed more than any blurred image could show. The transit exposed the planet's size and the atmosphere around its edge. The secondary eclipse isolated the light from the day side. The brightness pattern across the full orbit showed that heat and clouds were distributed unevenly, while the small deviation opened the possibility of an exceptionally rare reflective effect. We still do not have a map with clearly outlined clouds. No one can point to an image and say exactly where iron droplets are falling. But the planet is no longer a completely anonymous point of light. Its dayside, nightside, and twilight regions have each begun to leave their own signatures in the light reaching Earth. A world does not need to appear in a sharp image to reveal its climate. It only needs to move around its star, gradually present different regions to us, and change in brightness with each viewing angle. From that shifting rhythm, winds, heat, and clouds begin to emerge as the first lines of an invisible map. But on the map of WASP-76b, one region remains brighter than it should be. Near the boundary, where night gives way to day, Cheops detected an increase in light that rose more quickly than simple models predicted. It did not resemble a glowing storm or an eruption, but rather light, being reflected in a very specific direction. To understand why part of the atmosphere might send additional light toward Earth, we need to look more closely at that tiny rise in the curve, because sometimes a small excess of light within an otherwise ordinary pattern is enough to open the possibility of colored rings never before confirmed on a world beyond our solar system. That excess light did not appear as a flash suddenly bursting through the atmosphere, nor did it cause WASP-76b to become clearly visible through the telescope. It was only a very small section of the planet's brightness pattern, rising slightly above what the models predicted. Seen only once, the difference could easily have been dismissed as noise. But when the same feature continued to appear across repeated observations, it began to resemble a message returning from the same region of the planet. Cheops returned to observe WASP-76b over a period of 3 years, carrying out a total of 23 detailed observing sessions. The researchers also compared those data with measurements from TESS, Hubble, and Spitzer, allowing them to examine visible light, thermal radiation, and atmospheric features together. This combination made the unusual bright region much harder to dismiss as a chance instrumental error. Each telescope contributed a different perspective. Cheops followed extremely small changes in visible light, where reflection from clouds could leave a trace. TESS also measured the planet's brightness over multiple orbits, while Spitzer observed the heat it emitted at infrared wavelengths. Hubble added information about the atmosphere, helping the team test whether the signal might be connected to temperature, clouds, or some other structure near the planet's edge. When the pieces of data were combined, the excess light appeared near the eastern boundary of WASP-76b, where darkness gradually gives way to the illuminated side. This region is often called the morning boundary. Although on a tidally locked planet, there is no true sunrise sweeping across the sky as there is on Earth. The divide between light and darkness remains almost fixed. It is the gas, clouds, and material that continually drift across it. A current that has traveled across the entire night side reaches this region just before returning to the star's intense light. It may carry particles that formed in the darkness, cloud layers that have not yet had time to evaporate, and some of the heat retained during the journey around the planet. If there is one place where the atmosphere might differ from the rest of the world, the morning boundary is a natural place to begin looking. What drew the researchers' attention was not only that this region appeared brighter. The light increased rather quickly when the boundary rotated into a particular viewing angle, then failed to maintain the same intensity as the angle changed. This was the first time such a sharp variation had been recorded in the phase curve of an exoplanet, making a cloud layer that reflected light equally in all directions an incomplete explanation. Imagine a sphere coated in matte paint. As the sphere turns in front of a lamp, its brightness changes slowly and smoothly because the light is scattered in many directions. But if one part of the sphere has an unusually reflective surface, the brightness may rise sharply when that region reaches the right angle, then quickly fade when the alignment between the lamp, the sphere, and the observer is no longer favorable. WASP-76b seems to be telling a similar story. The excess light is not spread evenly across the day side, nor does it rise with the gradual rhythm expected from a broad hot region. It appears concentrated near one edge, and becomes more noticeable only within a fairly narrow geometric alignment between the star, the planet, and Earth. In scientific language, this is known as directional reflection. An object does not send the same amount of light in every direction, but reflects more strongly along a particular path. A familiar comparison is the brief glint on the surface of water when the sun, the lake, and the observer's eyes happen to align, even though the water has been there all day. This possibility led the researchers to a phenomenon known as a glory. On Earth, a glory sometimes appears as colored rings surrounding the shadow of an airplane, a mountain climber. A similar phenomenon has been observed on Venus, but it has never been securely confirmed on any planet beyond our solar system. If the bright feature on WASP-76b truly comes from a glory, the colored rings were not seen directly by the telescope. CHEOPS did not capture an image showing luminous circles surrounding a cloud. It measured only an increase in light at the precise angle where a glory-like effect might reflect more strongly toward Earth. That distinction is important. A direct image would reveal the shape, colors, and position of the rings. The current data are more like standing behind a wall and noticing that the light inside a room suddenly brightens when a mirror turns in the right direction. We may infer that something reflective is there, but we still do not know its exact shape or material. A glory is an appealing candidate because it can create a bright region strongly concentrated along the viewing direction. Light interacts with countless tiny particles or droplets inside a cloud, and waves traveling along slightly different paths meet again. At some angles, they reinforce one another. At others, they weaken the light. The result can be a series of alternating bright rings, although from Earth's distance, those rings would blend into a single signal. We do not need to follow every ray of light in detail to understand what makes this unusual. An ordinary cloud made of particles, with many different shapes and sizes, tends to scatter light in many directions, producing a broad and diffuse signal. For the light to gather into a more delicate structure, the particles cannot be completely chaotic. They must be similar enough for light passing through the cloud to follow a shared pattern. The droplets may need to be nearly spherical, relatively uniform in size, and able to survive within an atmospheric layer that does not change too quickly. On a planet with powerful winds, extreme temperature contrasts, and metals capable of vaporizing, the possibility of such order seems almost opposed to everything around it. That is exactly what makes the signal so compelling. WASP-76b is usually imagined as a turbulent world, where the day side heats matter into vapor and the night side allows metallic particles to condense. Yet near the boundary between those two regions, there may be a cloud layer stable enough for droplets to preserve similar shapes and sizes for a meaningful length of time. The signal was detected across observations spanning 3 years. If the same glory truly contributed light throughout that entire period, then the cloud layer producing it must either have lasted for a long time or have been continually replenished with new particles possessing similar properties. Either possibility suggests that beneath its violent appearance, the atmosphere contains a surprising degree of stability. The cloud may not preserve the same individual droplets for years. Older particles may fall or evaporate, while new material continually condenses within the same temperature region, producing droplets similar to the generation before them. A river remains, even though its individual water molecules do not stay in one place for long. The cloud layer may be maintained in much the same way. If the temperature near the boundary remains relatively stable, each current of gas passing through may reach the same condensation threshold. Newly formed particles may begin at similar sizes, then be held by the winds within the same atmospheric layer before they have time to grow too different from one another. A mechanism like this could create the uniformity required for a glory. Even if each droplet survives only briefly, iron immediately becomes an intriguing candidate for those droplets. We already know that iron vapor has been observed along the evening edge, while the signal weakens after the gas crosses the night side. If iron condenses into droplets in the darkness and is then carried toward the morning boundary, it could form a cloud layer precisely where the unusual light appears. The connection seems natural. The day side turns iron into vapor, the night side allows it to condense, and near morning, the newly formed droplets encounter starlight at a special angle. With only one final step, the metal rain and the multicolored glow could become two parts of the same atmospheric cycle. But an elegant story is not enough to become evidence. No measurement has directly established that the light-reflecting particles are made of iron. They may contain another metal, a heat-resistant mineral, or a mixture of several materials. Even if iron rain truly occurs on the night side, the cloud layer responsible for the excess light could belong to an entirely separate process. Liquid iron also raises many questions. At what altitude could the droplets survive before falling? Would they remain spherical within powerful winds? Or would they be stretched, collide, and break apart? Could a cloud of iron reflect enough light within the wavelength range observed by Cheops? These questions require observations across more colors before the answers become clear. Apart from a glory, the bright region could come from a highly reflective cloud layer that does not produce true colored rings. If the morning boundary simply contains more bright particles than the surrounding regions, its reflectivity could increase. Winds carrying clouds from the night side and then causing them to evaporate quickly as they enter the day side could create a narrow bright region near the transition. Imagine clouds that exist only within a thin band. Deep in the darkness, they do not receive enough light to be seen clearly. As they reach the boundary, the star begins illuminating the particles, causing the cloud band to brighten. Farther into the day side, the temperature rises rapidly, and the clouds disappear, preventing the reflective region from spreading across the entire hemisphere. A cloud band like this could cause the brightness to change fairly quickly, without requiring a glory. The difficulty lies in the precise shape of the curve and how strongly the signal is concentrated within a particular viewing angle. Researchers must compare many kinds of clouds, particle sizes, and spatial distributions to determine which model produces a light pattern most similar to the data. Temperature must also be considered as an explanation. The eastern boundary may contain a region hotter than predicted, emitting additional radiation and making the system brighter. But observations in visible and infrared light help limit this possibility. A broad, warm region would usually change the curve more gradually, while the observed signal appears sharper and more concentrated. A small hotspot could still exist if the atmosphere creates a vortex or an unusual wind current. Yet thermal emission does not depend as strongly on a narrow viewing angle as light reflected by cloud droplets. To explain the entire signal through heat alone, a model would need to create a hot region whose position, size, and timing matched the data extremely well. It is also possible that the climate model used for comparison is missing an important component. Upper atmospheric layers may absorb and emit light in ways that have not yet been fully described. Chemical changes between the two edges, overlapping cloud layers, or atmospheric escape into space could all make the phase curve differ from simple prediction. For that reason, the excess light was not tested with a single glory model and immediately labeled a rainbow. The research team had to explore many explanations, changing the heat distribution, reflectivity, cloud location, and the way light was scattered through the atmosphere. A glory emerged as a candidate because it could explain the signal's directional and concentrated nature. But it remains a hypothesis awaiting confirmation. What can be said with greater confidence is that the unusual bright region is present in the analyzed data. It appears near the eastern boundary and does not fully blend into the smooth brightness pattern expected from a uniform planet. The fact that Cheops observed it repeatedly over several years, supported by data from other missions, makes the feature more significant than a random fluctuation. What remains uncertain is the cause. The light may come from a glory, a localized bright cloud layer, a temperature difference, an atmospheric structure not yet fully modeled, or a combination of several processes. Science often advances within the space between those two statements. Knowing that a phenomenon is real, but not yet knowing which story behind it is the best one. That uncertainty is not a flaw to be hidden. It is the reason WASP-76b continues to be observed. Each explanation makes a different prediction about the color, timing, and changing shape of the signal. If a glory truly exists, the excess light may carry a distinctive color signature. If it is only a bright cloud, the reflection will vary, with particle size and composition in a different way. Observations across multiple wavelengths would be like placing different colored filters in front of the same source of light. A material may shine strongly in one color and almost disappear in another. By following the boundary across several bands of light, astronomers may gradually determine what kind of particles the cloud contains and which reflective mechanism is taking place. The signal may also change over time if the planet's weather varies. A glory created by a stable cloud layer may repeat in nearly the same location across many orbits. A temporary cloud or storm could cause the bright region to strengthen, weaken, or shift. Continued monitoring will reveal whether the boundary is a lasting structure or only an unusual moment in the climate of WASP-76b. Among the possibilities still open, a strange image begins to emerge. Gas from the night side carries particles toward the boundary, where starlight first reaches them. Tiny droplets suspended in the atmosphere may reflect light back into space. Only when Earth lies close to the correct direction does that reflection become strong enough to lift the phase curve slightly. No one on Earth sees the colored rings with their own eyes. We receive only the combined light after a journey of about 640 years, blended with the much stronger brightness of the star. Yet hidden within that tiny increase may be an intricate structure created by countless, nearly identical droplets inside a cloud beyond our solar system. If the glory is confirmed, it may become the first such phenomenon identified on an exoplanet. The discovery would offer more than a beautiful image for WASP-76b. It would reveal that the planet's clouds contain nearly spherical droplets of similar size, maintained within an environment more stable than its blazing appearance might suggest. A faint signal could therefore tell us far more than the temperature alone. It might reveal the shape of cloud particles, the persistence of an atmospheric layer, and the way material is replenished over time. From hundreds of light years away, humans may not only detect that a cloud exists, but also begin to infer how similar the droplets inside it might be. This is the most important payoff of the excess light. On an ultra-hot Jupiter, where winds carry metals across the boundary between day and night, there may be a cloud region orderly enough to create an extremely delicate optical effect. The planet's violence does not necessarily erase fragile structures. Sometimes, the harsh circulation itself may continually rebuild them. But before calling the signal an iron rainbow, we need to examine the glory itself more closely. It is often described as a set of colored rings, making it easy to compare with the familiar rainbow on Earth. The two phenomena may look similar from a distance, but the light that creates them follows very different paths. A rainbow opens into a broad arc as light enters water droplets and reflects within them. A glory usually appears as smaller concentric rings and depends strongly on particle size, the way light waves meet, and the precise location of the observer. That difference also helps explain why a glory beyond the solar system would be so rare and difficult to confirm. The bright region along the boundary of WASP-76b has brought us to the possibility of a distant ring of color. But to understand why it appears only at a special angle, why the droplets must be nearly uniform, and whether iron truly creates the light, we must separate the glory from the familiar image of a rainbow. Because sometimes, what looks like a rainbow among the clouds is born from an entirely different journey of light through a world. The light that may be appearing on WASP-76b is often compared to a rainbow, but that description only helps us picture it more easily. A glory does not stretch across the sky as a broad band of color. It usually appears as a set of small, closely spaced rings surrounding a single point, and it can be seen only when the observer is positioned at a very particular angle. On Earth, this phenomenon can sometimes be seen from an airplane window or from a high mountain peak. With the sun behind the observer, the shadow of an airplane or a person may appear on the clouds below, surrounded by thin rings of color. Those rings are not fixed within the cloud. They depend on the positions of the light, the water droplets, and the eyes observing them. A familiar rainbow forms when light enters water droplets, changes direction, and separates into different colors. A glory is more subtle. It appears when light interacts with countless tiny droplets, and those different portions of light combine in a way that becomes clear only at certain angles. An observer who moves to a slightly different position may no longer see the colored rings at all. This difference helps explain why the bright region on WASP-76b intensifies during only a narrow part of the orbit. The planet, the star, and Earth must be aligned closely enough for the reflected light to travel toward the telescope. A small change in viewing angle may cause the signal to weaken, even if the cloud remains in place. A glory also cannot be produced by just any cloud. If the particles differ too greatly in shape and size, the light will scatter irregularly, and the colored rings will lose their definition. The droplets responsible for this phenomenon usually need to be nearly spherical, relatively uniform in size, and stable enough to create a consistent signal together. This is the most puzzling part of the possibility on WASP-76b. The planet's atmosphere is filled with powerful winds, extreme temperature contrasts, and clouds that may continually form and disappear. Such a turbulent environment would seem poorly suited to maintaining countless similar droplets, yet the excess light suggests that one cloud region may be more stable than the surrounding atmosphere. Those droplets would not necessarily need to survive for years. They could be formed continuously as gas passes through the same temperature region. Older droplets may fall or evaporate, while new ones appear at nearly the same size. The cloud layer could remain in place even though the individual particles within it are constantly being replaced. Glories are not found only on Earth. A similar optical structure has been observed within the thick atmosphere of Venus. This shows that such rings can form on a world very different from our own, as long as its clouds contain suitable droplets and the viewing geometry is precise enough. WASP-76b shows several signs that fit this picture. The light increases near the boundary between day and night, remains concentrated within a narrow range of viewing angles, and does not perfectly resemble a change caused by temperature alone. But the signal is still only a small feature within the phase curve. No image has revealed actual colored rings resting above the planet's clouds. The material forming those clouds also remains a mystery. Liquid iron is an intriguing possibility because the day side is hot enough to turn iron into vapor, while the cooler night side may allow it to condense. Newly formed droplets could then be carried by the winds toward the morning boundary, precisely where the unusual light has been detected. If those iron droplets were nearly spherical and sufficiently uniform in size, they might reflect light in a distinctive way. When Earth moved into the correct viewing angle, that reflection would become stronger and cause the light curve to rise. The image of iron rain and a glory would then become two parts of the same atmospheric story. Even so, no data have yet confirmed that the cloud producing the possible glory is made of iron. The droplets may contain another metal, mineral particles, or a mixture of several materials. An ordinary bright cloud layer could also contribute to the signal, even without creating complete colored rings. The phrase metal rainbow is therefore beautiful and memorable, but it is not a scientific conclusion. A more accurate description is that WASP-76b contains a region of unusual reflected light, with several characteristics consistent with a glory. Iron may be involved, but the true material composing the particles has not yet been identified. Even the precise location of the cloud layer remains uncertain. It may lie high in the atmosphere, where starlight can reach it easily, or within a deeper layer that is still bright enough to influence the phase curve. The size of the droplets, the thickness of the clouds, and how long they survive cannot yet be measured directly. The winds make the question even more intriguing. They may carry cloud particles rapidly around the planet, stretch the cloud layer, or mix it with surrounding gas. For a glory to continue appearing, the atmosphere must either hold the particles within a relatively stable layer, or continually produce new droplets before the older structure is destroyed. If the signal is confirmed, the most remarkable result would not be only the colored rings. It would also show that an ordered region can exist within an atmosphere that appears deeply chaotic. Tiny droplets may form at nearly the same size, remain suspended at a similar altitude, and reflect light according to a pattern clear enough to be detected from nearly 640 light-years away. But the bright region may instead be only a highly reflective cloud layer along the morning boundary. Gas arriving from the night side could carry cloud particles into the transition zone, where they begin receiving starlight, then quickly evaporate as they move farther into the day side. A narrow cloud band like this could also cause the brightness to rise and fall over a short interval. An unusual temperature region cannot yet be ruled out entirely either. Winds may create a zone hotter than predicted, or current models may not fully describe how heat is distributed through the atmosphere. However, thermal light usually changes more gradually, while the observed signal appears to depend quite strongly on the viewing angle. For that reason, a glory remains one of the most compelling explanations, but it is not yet the final answer. It fits both the shape of the excess light and its location near the boundary between day and night. Other possibilities remain, waiting for additional data to either support them or rule them out. The beauty of this discovery does not lie in having a certain answer. It lies in the way such a tiny amount of light can narrow down what may be happening inside a distant atmosphere. The signal suggests that this region could contain a special cloud layer, with particles that reflect light very differently from the rest of the planet. A point of light too distant to resolve has allowed human beings to begin inferring the shapes of the cloud droplets within it. We do not yet know what those droplets are made of, but the changing light suggests that they cannot be completely chaotic. That alone reveals a surprising degree of order within the extreme climate of WASP-76b. If the rings truly exist, They may be appearing near the place where darkness meets the light, above atmospheric layers where iron may be condensing. No one has seen them directly. Only a small portion of light has left the planet, traveled through space for centuries, and finally reached our telescopes. To determine whether that light truly comes from a glory or merely resembles one, astronomers will need to observe it across a wider range of colors. Every material reflects and absorbs light in its own way, so the composition of the cloud may become recognizable once the data are detailed enough. The final question, then, is not only whether the luminous rings exist, we also need to know whether the mysterious cloud layer is made of iron, minerals, or some other material never before observed under conditions like these. And the answer may be carried within the next photons that more powerful telescopes collect from that distant boundary. Perhaps the answer to that glowing ring is still traveling toward us, carried within photons that left WASP-76b centuries ago. Each photon holds only a tiny piece of the planet, a color of light, a direction of travel, and the faint trace of particles it encountered along the way. On its own, it tells us almost nothing. Only when countless photons arrive together does the story begin to emerge. One of them may have left the planet from the region between light and darkness. Behind it lay an atmosphere hot enough for iron to exist as vapor. Ahead lay the cooler dark side, where metals could begin gathering into tiny particles. Somewhere between those two regions, the photon passed through a cloud whose composition remains unknown. Perhaps it encountered a droplet of iron, or perhaps it met a mineral particle, a droplet of another metal, or a cloud layer completely different from anything we currently imagine. After that brief encounter, the light changed direction and continued across space, carrying no image and offering no explanation, preserving only a slight alteration in its own color and brightness. Nearly 640 years later, that photon reached a telescope orbiting Earth. It blended with millions of others, becoming one tiny point within a stream of data collected across many orbits. When all those measurements were placed together, astronomers noticed that one edge of WASP-76b appeared brighter than expected. That was where the possibility of a glory began to emerge. We still have not seen the actual colored rings. No clear image shows a rainbow resting above the planet's clouds. What we have is only a small excess of light appearing near the position and viewing angle where a glory might form. The clue is intriguing enough to keep following, but not yet strong enough to close the story. To understand where that light truly comes from, astronomers need to observe WASP-76b across a wider range of colors. An iron cloud would not reflect and absorb light in the same way as a mineral cloud. Every material leaves its own signature, although the differences may be so subtle that only extremely sensitive instruments can detect them. Telescopes such as James Webb may help search for those signatures in infrared light. Webb cannot photograph individual cloud droplets, but it can look more deeply into the atmosphere's composition and temperature. Across repeated orbits, scientists can compare the day side, the night side, and both boundaries to determine where clouds are present, which regions are hotter, and where light is being reflected in an unusual way. If the bright region appears nearly the same after every orbit, that would suggest the cloud layer is relatively stable. If the signal strengthens, weakens, or shifts to another location, the planet's climate may be changing more rapidly. A long-lasting glory would not require the same droplets to survive for years. The cloud would only need to keep producing new particles of nearly the same size. The image is somewhat like a river. The water at any one location is always changing, yet the river keeps its shape because new water is continually flowing through. On WASP-76b, older droplets may fall or evaporate, while currents from the night side deliver fresh material. If the temperature near the boundary remains stable enough, the cloud layer could be rebuilt again and again. Iron is the most obvious candidate to consider. The day side is hot enough for iron to enter the atmosphere as vapor, while the cooler night side may allow it to condense. Newly formed droplets emerging from the darkness could be carried by winds toward the morning boundary, precisely where Cheops detected the unusual light. The story fits together beautifully. Iron evaporates under the starlight, is carried into darkness by the winds, condenses into droplets, and then reflects light as it returns toward the dayside. Iron rain and the glory would no longer be two separate mysteries, but two moments within the same atmospheric cycle. Yet nature does not have to follow the most elegant story we can imagine. The cloud producing the bright region may contain no iron at all. It may be made from several materials mixed together. Or it may lie within a different atmospheric layer from the one where iron is condensing. The signal could also come from a bright cloud layer that produces no complete colored rings. The altitude of the cloud remains another major question. If it lies very high in the atmosphere, starlight may reach it easily and reflect strongly back into space. If it lies deeper, the gas above may obscure or alter the signal before the light escapes. Even a small difference in altitude could determine what the telescope is able to see. We also do not know how far the droplets fall. They may sink only a short distance before reaching hotter gas and evaporating again, or they may continue downward, leaving the region that starlight can penetrate entirely. There is no clearly defined ground to mark the end of the rain. Below the cloud layer, the atmosphere grows denser and heavier. Pressure rises, and temperature may change in ways unlike the conditions above. An iron droplet, descending into those depths, may dissolve into the gas, enter another state, or be carried elsewhere by deeper currents. Its journey would continue, but without leaving a signal that human beings can easily observe. Some of that material may eventually return to the dayside. As temperatures rise, the particles may turn back into vapor and blend once more into the atmosphere. Winds then carry them toward twilight, beginning another journey around the planet. If this cycle truly exists, WASP-76b has a form of metallic weather that never stops. But not every iron atom follows the same complete path. Some may fall deep and remain there for a very long time. Others may continue drifting through the upper atmosphere and return to the dayside. Some particles may remain trapped within clouds, while others are destroyed by heat before traveling very far. The atmosphere does not operate like a simple machine with only one route. It is more like a vast network of wind, heat, and clouds, where each current may carry material in a different direction. That complexity is what makes reading the signals from WASP-76b both difficult and compelling. Future missions will not study this planet alone. As more hot Jupiters are examined in the same way, astronomers will be able to compare them with WASP-76b. Some planets are hotter, some have cooler night sides, and others may contain very different clouds. Through those comparisons, we may learn whether glory-like bright regions are truly rare or simply very difficult to detect. Many planets may have cloud layers capable of producing similar effects, while Earth rarely happens to lie at the correct viewing angle. A glory depends strongly on the positions of the star, the planet, and the observer. Only when all three are aligned in nearly the right way can the light become concentrated strongly enough in our direction. If WASP-76b remains the only known case after many years of searching, that would make the planet even more unusual. Perhaps its temperature, wind speed, and cloud composition create an exceptionally rare balance. Iron can vaporize on the dayside and condense in the darkness, while a cloud layer near the boundary survives long enough to reflect the starlight. Along with clouds and rain, the atmosphere of WASP-76b may also be slowly escaping into space. The planet orbits extremely close to its star, where intense radiation and stellar winds constantly act on the upper layers of gas. Some material may be pushed away, forming a thin stream that we have not yet measured completely. This process would not strip the planet's atmosphere away in a single night. It unfolds very slowly, perhaps over millions of years. Only a small amount of material escapes at any given moment, but across immense stretches of time, the planet's shape and composition may gradually change. No one knows what WASP-76b will become in the distant future. It may retain most of its atmosphere for a very long time, or slowly lose its outer layers under the influence of the star. That question does not directly determine whether the glowing rings exist today, but it reminds us that the planet is not an unchanging world. Clouds are forming and disappearing. Iron may rise as vapor, condense, and fall. Winds carry the atmosphere around the planet, while a very small portion may escape into space. WASP-76b is changing across many different timescales, from the few hours of a rainstorm to the millions of years over which its atmosphere is worn away. Looking back across this journey, perhaps the greatest value of WASP-76b lies not only in the image of iron rain. The planet shows that human beings can study the climate of a world we have never seen as a clearly defined sphere. We receive only light, but within that light are traces of heat, wind, metals, and clouds. When the planet passes in front of its star, the transit reveals its size and the composition of the gas surrounding its edge. When it disappears behind the star, the missing light tells us more about the day side. During the time between those two events, tiny rises and falls in brightness reveal where heat is concentrated and where clouds may be reflecting starlight. The planet's two edges also show that its atmosphere is not the same everywhere. The evening edge carries a clearer signature of iron vapor, while the morning edge appears to have lost part of that signal. A distant world begins to take on structure, no longer just a dark point passing in front of a star. The original question now has a fairly clear answer. WASP-76b is hot enough to turn iron into vapor, but not every part of the planet has the same temperature. When atmospheric currents carry iron vapor away from the dayside and into darkness, the cooler environment may allow the metal to gather into tiny particles. Those particles may grow into droplets and fall into lower layers of the atmosphere. If some of them are relatively uniform in size and occupy the right region near the boundary, they may also contribute to the glory-like excess light detected by Cheops. This is how a world hot enough to vaporize iron can still have metal rain and a delicate ring of light. There is no true contradiction between fire and liquid droplets. They simply exist in different regions of the same planet, connected by enormous winds. But the final answer is still missing. We do not know whether the droplets producing the bright region are made of iron. No one has confirmed that the colored rings truly exist. A glory remains a compelling explanation alongside other possibilities, including bright clouds, temperature variations, or an atmospheric structure that is not yet fully understood. Perhaps this is the most fitting way to close the story of WASP-76b, not with a certain declaration, but with an image that remains open. Along the twilight boundary, hot gas continues drifting into darkness, carrying metal atoms that have only recently left the illuminated side. A little farther away, the temperature falls. Tiny particles may begin to appear within the atmosphere, meeting one another and slowly growing. Some continue drifting inside clouds, while others quietly sink into deeper layers where starlight can no longer reach them easily. Near the planet's edge, a photon passes through the cloud layer. It strikes a tiny particle, changes direction, and leaves WASP-76b behind. No one knows whether that particle is made of iron, minerals, or some other material. The photon carries no name for the phenomenon that has just occurred. It carries only light. Nearly 640 years later, that light reaches Earth and adds one more small point to the curve we are trying to read. A single point cannot tell the entire story, but it is enough to suggest that something remarkably delicate may exist within that blazing atmosphere. On that distant world, iron may still be falling through the darkness. Above the deeper atmospheric layers, a faint ring of light may be appearing whenever the star, the clouds, and Earth move into the correct alignment. It may be the first glory ever recognized beyond our solar system, or the signature of another phenomenon that humanity has not yet learned to name. Until the next photons bring us more clues, that luminous ring will remain at the boundary between fire and darkness, waiting for us to understand what it truly is.